Alrighty. Hello, everyone. Welcome to OCP Tech Talks. This is our first server session. I'm Kaylee Burdett. I'm the Director of Global Events for OCP. Before we get started, I just wanted to go over a couple housekeeping items. You've entered the Zoom today muted, so please stay muted if you won't be speaking, so we can just eliminate any background noise. This session is going to be recorded, and we will post the recording to the OCP past events page once the event is over. And if you have any questions during this webinar, please either type them in the chat or you can address them to the speaker directly. You can come off mute and ask your question, but please just wait until the speaker has finished their specific talk. They've built in time for Q&A at the end, and that way it'll go a little bit smoother if we don't have multiple people talking at one time. I also wanted to thank our sponsors today. Google, Meta, and Intel have made this Tech Talk possible, so thank you so much for that. And I'll also be on the webinar today, so if you have any questions about OCP, you can pop them in the chat and we'll be here to help you. And with that, I'm going to pass it along to John Stewie.
Yes, good morning and good evening, everybody. I'm John Stewie, the co-lead for the OCP server project. I'm here along with Mark Shaw. I'd like to thank everyone for attending today. This is day one of the talk. We have today and tomorrow, so got a lot of content coming up in the next couple days. So today will be the subproject updates with extended ODSA panel and extended OAI panel. Looks like my slide didn't get updated here. And then tomorrow we'll be focusing on the modularity with the introduction of the DC MHS series of specifications, which has gotten a lot of interest. Little history on the server project. Obviously we deal with the servers and all their peripherals and chassis. If you're not familiar with how OCP is structured on the website, if you go to projects, you can see all of the different projects. So this one is server, but all the other projects are here under the projects tab on the OCP website. We do have 4 sub-projects that will all be presenting today. The HPC or high performance computing sub-project, the OCP NIC 3.0 sub-project, the Open Accelerator infrastructure project, and the Open Domain specific architecture sub-project. So we've got a lot of content from all of these presenters. Glad we could all get together today to do this extended presentation. The public call details from all of our sub-projects are in the main OCP calendar, with just the server ones in a server calendar. All the decks will be online after the presentations. You can go in and click all these links to get to these calendars and find the call links for all of our calls. They're all out there, so if you know where to look at the calendars. All the documents that we cover in our monthly calls are in the server working wikis. So there'll be some files posted there for, I don't think there's anything from today's link, but there will definitely be for tomorrow's meeting. We have a good agenda today. Once again, thank our sponsors for Google, Meta, and Intel for helping sponsor today and keep all the costs down. Apologize for the dog in the background. Anytime someone walks by, she has to let me know. So today we're starting out with the OCP NIC 3.0 subproject with Damien, and with an update on the Gen 5 test fixtures with Jason Rock. Then we'll move on to the OAI. There's 3 separate presentations for OAI, followed by Alan with the HPC subproject update, which is going to be a shorter one. And then the ODSA subproject updates actually has a panel covering a lot of different aspects of ODSA. So I'll let Bappy go into the details about what all these panels are. followed by a wrap up. Unfortunately, I didn't put a break in here. So if you need to take a break, feel free to walk away and come back for a few minutes. I didn't realize I scheduled a 3-hour solid without a break today. But with only the presenters, that shouldn't be too much of a problem because no one's presenting for that long. Does anybody have any questions or comments before we get started with the OCP NIC 3.0 session? All right. With that, I will pass it over to Damien. Let me stop sharing so he can start. And it's all yours, Damien.
Thanks, John.
I don't know who's starting. You're muted if you're talking, Damien.
Can you see the screen?
Yes, we see it.
Great. I'm just moving the Zoom away. Cool. Hi, I'm Damien Chong, OCP NIC subgroup lead. Today, I'll be joined by Jason Robb, principal engineer at Dell EMC, to talk about the OCP NIC 3.0 activities and also the next-gen updates. Over the past few months, here are the OCP NIC subgroup activities since we last shared in the OCP Global Summit. We are working on the tall small factor thermal test fixture. It is a modified from our existing small factor test fixture because now we support the tall small factor. They are modified by 3 different components to convert this to support tall small factor. The mechanical and design files are all posted in Wiki. You can take a look. And Jason and his team is working on the PCIe Gen 5 enabling for this. Some companies have used the thermal test fixture and it works good in this area. Next, we are also working on the PCIe Gen 5 SI test fixture to ensure the system and the NIC compatibility. This is usually done in any PCIe system. We do have our own compliance load board, which Jason and his team design is currently in the lab. And we will have the compliance base board to be designed soon. These 2 areas, Jason will bring us through the details in the subsequent slides. The next subgroup also work on thermal modeling because when we first engaged in the tall small factor thermal discussion, the team found that we don't have quite a common ground into like where the sense point is when we say about temperature, where do we mean, where it's being measured. And different cable companies, different vendors have different assumptions. And you can see some of their work in the QSP-DD active cable modeling work that they show in Global Summit. Now they are working on the OSFP IHS cable modeling, which is supported by the enabling of the tall small factor NIC. Of course, when we develop a model, we have to validate the model to ensure there's accuracy. So this is an area will be the subsequent focus area for the thermal group. And last but not least, as a group, we also look into the next gen speed. For example, the PCIe Gen 6, we'll talk more about later, is currently in the Ref 1.0 base spec, as well as we'll talk more about the RMI-based transport as well. Next, I will pass it to Jason to bring us through the details of the PCIe Gen 5 thermal test fixture.
Hey, thanks, Damien. And also thanks to Google, Meta, and Intel for hosting this. This is really going to be a good session. So for the thermal test fixture, if you look through the OCP NIC spec for version 3, we had defined a thermal test fixture. The main goal of that is to provide a common model for people to develop both a server, a card, and as well as a system. This was originally designed back when we were generating the specification, moving it towards 1.0. At the time, we as a group were focused on Gen 3 and Gen 4 PCIe speeds for that, but we did have some foreboding on what we wanted to do for PCI Gen 5. So for the Gen 4 version of the TTF baseboard, we did design this PCB for 32 gigatransactions per second speeds. So we did use very low loss material for this design. The one thing, the way the TTF works, so it looks, as you kind of see in the top right picture, it kind of represents a slot within a server. So that's a defined model. And usually you plug that into a fan or some sort of airflow. And then there's a cabling that goes below it that extends from a server. So you're having the ability to generate traffic. For Gen 5, what we used for Gen 4, we had a Gen 4 cable assembly. We're right now working with a couple of vendors to get specified a Gen 5 version of that. That's not commonly available right now. So we're in the process of working with 2 vendors to get that sourced. Once we get that in the lab, we'll then be able to confirm whether the TTF can operate at Gen 5. So that's kind of the current status with this. But the whole goal of this is to have a common thermal test fixture so that there's not a lot of different variations that have to be procured. And then on the next slide, so this was thermal focus. One of the other important areas with PCI is the signal integrity. So we also have test fixtures for that too. As I said before, with the version 1 of the standard, and we're already now at version 1.2, there was a focus on Gen 3 and Gen 4. The CLB Gen 5 is based on the CLB's Gen 4 version. So it is a new design. We had to move that to another low loss material to meet the tolerances of what's required. I think everyone's aware of the supply constraints in the market. So we did Gerber that in January. Finally, the PCBs for that arrived in March, and then we finally got it assembled just last month. So we're currently testing it right now, looking at if it's going to meet the impedance models for what we need to do. Everything so far is looking pretty good, and we may have at least a viable card that can be used with potentially some changes to some S modeling if someone has to use that early on. We will have results from this, hoping by next week's, we have a monthly call, and hopefully we'll report some of those results in our next week's call. So the CLB, these are used, load boards are used for plugging into servers to test the servers routing. The CBB, which is the compliance baseboard, these are used to test the NICs themselves. So it provides a way to break out the signals for NICs. The same deal, it's going to be based on the current 4.0 design. We also have to do some updates for PCIe SIG. So they are now requiring some features like the split spectrum as part of conformance. So those have to be signals updated for that. Once we start getting some results from the CLB, we'll take that information and we'll start routing the CBB. So we're hoping to have that started here, as you heard, probably next month on the routing portion of that. Damon, I think, and the last thing I'll say too, if you see the picture, I didn't mention that too. So the CLB comes in a four assembly pack. So there's 2 cards, enough to get the breakouts, CBB board 1 and 2, to get the breakouts of all the 16 lanes. And then you have a calibration board to base it off each CLB, and then an impedance coupon. And then lastly, to both the CLB, CVB, and then also even the thermal test fixture. So the CVB and CLB, the Gen 3 and Gen 4, you can actually obtain these from UNHIOL. They have these available for sale. We're also working with them to have the ability to sell the TTF Gen 4 and then eventually Gen 5, as well as the CLB Gen 5. They're looking to sign up for that as well. So, Damien?
Yep, good coverage. Thanks, Jason.
No problem.
Next, we're going to talk about the next gen speed bump that the work group is working on. So as we mentioned earlier a little bit, that we are looking for support PCIe Gen 6. And we have looked into the difference between PCIe Gen 5 and Gen 6. The major difference, how do we bump up the speed, is through a different encoding scheme. PCIe Gen 5 run on NRZ, and PCIe Gen 6 run on PAM4, which basically means every UI will transfer 2 bits on Gen 6 as compared to 1 bit on Gen 5. The Nyquist frequency between the two transfer are the same, and the team have looked into it, and it appears that we can continue to support this on the SFFTA102 connector, which is what the OCP NIC 3.0 is based on. However, we do realize a couple of things. So the insertion loss and crosstalk for 64G PAM4, which is what Gen 6 is using, is yet to be in the spec. However, we do have enough members in the OCP NIC subgroup to be a member of SNIA to make this modification once we align on what is the crosstalk guidance we would like to implement in the SFFTA102 spec. For SNIA to restart or edit this project, we need 3 SNIA members to modify. So we do have enough members for that. In our next meeting, we will talk about the potential crosstalk. And if you're interested, you can join us. It's actually happening in the very first week of the month. The second part I would like to talk a little bit is about investigation on the faster hour band. We heard this from the offline conversation, OCP Global Summit, as well as server group discussion, that whether there's any potential we can improve our hour band speed from the supported 100 megabits per second to something higher. This is the area that we look at. We have a bit of discussion, but there is no low-hanging fruit. The reason is to support more than I/I, we can go to either maybe RGMII or SGMII that are either having a challenge of more pins that's not backward compatible, or more pins we don't have enough pins. We are looking at tunneling feature as well. But very unfortunate, our pin definition only support USB 2, so we don't even have USB 3 tunnel to as the RGMI capability. We have 2 spare pins that we have some idea about how about using those spare pins as a mode. But this is an area that we're still looking at, and it's very important that backward compatibility is a priority. We want to make sure that the new gen NIC will be able to plug into existing gen server while we do this. Based on what we see so far in our investigation, the form factor for the OCP NIC 3.0 to support the next gen speed bump, including PCIe Gen 6, is no change. Our small form factor, large form factor is there, and the newer tall small form factor have enough headroom to take care of additional thermal challenges from the speed bump of PCIe Gen 6, which potentially support up to 800G service. This will be a good segue to promote a little bit about a tall small factor, which is our latest small factor that we shared last year. The difference between tall small factor and small form factor is a 2.7 millimeter taller height, which is make up a total of 70.8 millimeter. That additional height allows a couple of things. It allows for taller ASIC heatsink. It allows for QSFP-DD with add heatsink. It also allows for OSFP HGX to be supported on the NIC cases. And as we know, on the ARG front, OSFP does have a lead. And for non-NIC use cases, this form factor also support things like mini SARS HD. And with this form factor, we also develop our thermal test fixture to support it, which is then seen on the right. The specification of reference part 2 already included TSFF support. And for those looking for the modification file for your own thermal test fixture to support TSFF, they are actually in our wiki. As every work group, we will need your support to give us feedback whether we are heading in the right direction. So for this, we do have a feedback to OCP NIC as a URL below for you to engage with us. You can send us email, I get it from time to time. You can send us feedback through the form, such as bug report, comment, any suggestions, new feature requests, put into the tool, put in the form, we definitely would like to hear your thoughts and feedback to improve the overall experience and the ecosystem. And the call to action today will be join our discussion. Our meeting held every first Wednesday of the week at 11 a.m. Central, 9 a.m. Pacific. And do provide feedback, as I mentioned earlier, and drop by our wiki to look at our specification, our collaterals, thermal test fixture, sugar test fixture, our meeting minutes are all in our wiki. With that, remember JFW or JFK. Yeah, these are the call to action that we help, that you can help us in this area. For now, Jason and myself will take any question that you have. See what's in the chat. Basically, it's a welcome message.
As we're queuing, one thing that Damien mentioned too about the tall small factor form factor for the thermal test fixture. For that, it's just you just change out the front panel of it. It's two pieces of sheet metal that just gets swapped out, so you can still leverage that with the main base part of it.
Yep, that's right. And there's a picture for it. Yeah, we do have NIC companies try that. Yeah, and it's been working fairly well. And something we did not mention is there's a change of how we set up this thermal test fixture. In the small factor, we set up in such a way that their typical use case on top is a PCIe cam card, and below is a small form factor NIC. Yeah, but when we think that in terms of like a tall small factor use case, it could be two small factors stacked on each other. So this is the being developed in such a way. Any question from the floor?
Doesn't sound like it. We've got a few more minutes, Damien, if you want to bring up and show everyone on the wiki where these documents are. There's got a lot of new people here who probably don't know where to go find the specifications.
Sure.
Anybody else has any questions or comments, please hop in.
Let me share my.
Hey, Damien, you see the question from Robbie. Will the future spec be updated to enhance coverage on the hot swap design?
Let's see. Ravi, yeah. Will the future spec be updated to enhance coverage on hot swap design? This is an area that any specific enhancement area that Ravi you're thinking of? I think with an enhancement, I think we need a so-called problem statement to start with. As far as I know, yeah, Meta do have some design that also capable. So yeah, based on that, we think there's a path that definitely, I think since you brought the question, you do see some area that probably is not as adequate. Would like to know more, and definitely if there's an area that you can point out where you would like to see us to improve on, like hot swap, and if you give us a problem statement, yeah, I think that is something that the team can work on.
Yeah, thanks. I'll follow up offline with you, I guess. So basically, so we have notations in the spec. It is not in the scope of the spec, and there are any particular considerations in terms of the timing requirements for hot swap. It's like we have some coverage. There are some cautions on that. So I guess that's where I was going with this, Damien.
Sure. Yeah, I don't think we define any timing on the hot swap. Yeah. Yeah, we'll definitely would like to see what are your thoughts, and definitely something to work on.
Thank you.
Yeah, definitely. Thanks.
All right. Thank you, Damien. Thank you, Jason.
Thank you.
Okay. Pass back to you, John.
Yep. So next up, we have 3 different OAI presentations. Who's going to present next? Is it Sung or Bichan?
I'm going to present.
Okay.
Yeah,
go ahead and start sharing them.
Okay. Can you see my screen, John?
Yes.
Okay,
good. Go ahead.
All right. Hello, everyone. My name is Song. I'm with Intel. I'm also the OAI high-speed and the system workstream lead. Here I have Bichan with me as well from Meta. He's going to talk about the SI challenges in the work that we have done in the high-speed and the system workstream. Okay. We're going to cover 5 topics today, right? The first one, we're going to talk about the scope of the OA work group for 2022. And the next one is that I'm going to provide update on the OAM, UBB, and the expansion card. And last, Bichan is going to talk about the SI challenges that we have seen while we're developing the spec from the OEM to the OEM and the OEM to the expansion card. Okay. So this is the milestone, right, of what we have been doing from the OAI. And for the 2022, we actually just published the OEM UBB 1.5 in last quarter. And in the next 2 quarters, the work stream, the work group, right, is going to be focusing on the OEM 2.0 and UBB 2.0 and the expansion card 1.0. So I think the also the those are the feature that we're going to targeting for the spec is the 112 gig PAM4 PCI Gen 5 Gen 6 and the OEM to be a 1 kilowatt, and this at the system level for the OEM, and also for the expansion card is going to be like air, liquid cool, or hybrid cooling as well. All right. So just give you some update on the OEM 2.0. We have been working on this project since last year, and what we come up with is that the dimension for the 2.0 is going to be 170 by 102, which is an increase of 5 millimeter from the previous generation. The previous gen is a 165. And we also locked down the voltage input for the OEM as well. And we have either 54 or 48 volt and 3.3 volt. And we get rid of the 12 volt because by looking at the application, right, we are targeting for high power, and 12 volt is no longer efficient to deliver such a high power for the OEM. And the TDP of the OEM is going to be 1 kilowatt, and we're actually adding a dual power entry. So it depends on the design. You can either stay with one power entry or dual power entry for higher power. And the EDP target for this OEM module is going to be ranging from 1.2x to 2.0x. Okay. And we also adding flexibility on the stacking connector, the height for the OEM to the UBB. So we're adding an option that depends on the power delivery design, or if you need to have a more space underneath the OEM, then you can go with the 5 mm spacing. So it creates flexibility, depends on the customer design. If you are more focusing on the SerDes or power delivery, you can have some trade-off there. And the SerDes speed is going to still targeting for the 112 gig PAM4 long reach, and also the PCI Gen 6. So for the UBB update, we are still working on defining lockdown the final form factor. But what we have right now is we are targeting for 655 millimeter by 417, which is a slightly increase from the previous generation. The previous gen is a 585, and we try to increase it to 655 mm. And there's a reason for that, because we are going to adding more feature on the UBB, like supporting the root of trust security module, and also we're supporting the same the 170 by 102 OEM, 8 of them, and also it can support up to 8 extended expansion module as well. And the last budget still the same for 28 gig. We are still targeting for 28 to 30 dp. Depends on the OEM and the expansion module design. You can have some trade-off and to optimize the routing. Okay. And in terms of the last budget from OEM to OEM, and the OEM is going to stay at the 8 dB, and the expansion module, the card is going to be targeting for 6 dB. Okay. Next, this is a new platform that we have been looking into and develop, and it's called expansion card. And right now we are going to target for the 1.0. So the card itself is going to be the dimension is going to be 160 mm by 150, and it also support the 2 power input, 54 volt and 3.3 volt. And the TDP of the card, it depends on the usage and in terms of the cooling of the system. And right now we are going to target up to 400 watt for different configuration, and depends on the application. So there are 2 config that the workstream is currently looking into right now. One is called the file retimer config. So it is going to be TDP is going to be up to 200 watt with 1 high-speed connector. So the high-speed connector is a 4x8 SerDes input, and at the same time, the same module is going to support the 4x8 scale-out port. And for the switch config, I think the switch is going to be consume more power, depends on the the standard that the design that you try to do. So we are going to push more higher power for the switch. We're going to target for 400 watt, and also we're going to adding double the SerDes input to be 8x8 input. And the scale out is going to stay the same. It's going to be a 4 scale out with by 8 SerDes thing. And the expansion card not only can support these two config, it can also support other config, depends on the usage. It can be a NIC based, or it can be a remote memory, and it can be other config that for different application. So we are not really locking down what needs to be done, but we create a flexibility that any of the config that you can implement based on your usage. All right. So the next thing is that these are the two config that I mentioned before that we are the workstream has been focusing on. The first one is the retirement config, and we have done quite a lot of the SI assessment and also looking into the power delivery as well. And at the same time, also looking for the mechanical, like the ejector mechanism, right? And also looking into the UBB tray, how you can do plugging into the system, and what is the ease of use, serviceability, those kind of things that the workstream has been looking into right now. And these are the two config. Now, the first one is that if you want to go with the retirement config, you can use a single connector instead of two, and it is going to be form factor compatible. So if you want to go with a switch to adding more SerDes lane, then you will have the flexibility to add another connector as well. All right. I would like to have the B-Chan to cover the SI challenges, and he's going to be B-Chan is the main key contributor into the workstream. Yeah, he's been leading some of the SI activity with other team member and also external vendor as well. Okay, B-Chan.
Thank you, Song, for introduction of me. So as Song mentioned, we have two style, right? One is PHY retimer, the other is switch. We did some example routing to help people to guide through, what is a PHY retimer routing and what is challenge and what is switch config routing. So right now in this presentation, we focus on the PHY retimer config. We did some example. We did layout, we did post layout, fabrication, simulation, and we did some fabrication of the scale up card with the class 8 material, latest class 8 material, and did the measurements. However, in today's presentation, I'm going to present the example of the SI, full wave simulation, which is post layout simulation, and compliance with the COM, by IEEE 802.3.ck, right? Because that's the equivalent to 112 GLR. Next slide, please, Son. So we did the two examples, one of the longest trace for scale up, the other is the scale out longest trace. As in our example, we did an actual layout. We found it out that longest trace on the scale up, which is OEM to OEM, will be wind up at 13.5 inches. Then we use the 800G, the class 8 material. I did couple of investigations in other projects, and we selected EM892K2. We have Maxron Edge. We have DJ L2 plus, with the L2 glasses to get a medium value of loss is 0.85 dB per inch. Even though that if we twitch the stack up, we can get a lower loss. However, due to the thickness of the whole board, we cannot change too much. So we put the average value here, 0.85, medium value here to estimate, which wind up the worst case scenario of UBB loss at 11.5 dB. Well, if we have better material, of course, we can get better results, right? The scale out, for the longest trace, the scale out here, the example we did is from OEM to the retimer. If we remember, one of the topology in the previous slides is it has to go through the OD connector. It has to go through the mezzanine connector. all the way to the extension card, to the retimer, to the LR capable retimer there. So we talk with a couple of the SerDes IP in the market for 112G. Most of them are actually the switch network switch major players. With their package and with their ping map, we did actual layout on this one. So the scale out wind up that the longest trace will be at 20 inches. Use 0.85 as a empirical value, dB per inch empirical value. Wind up at 17 dB on the UBB itself. So please go to next slide. Again, the longest trace will be the diagonal, right? So from your leftmost, OEM to your rightmost OD connector or expansion card, right? So we consider those worst case scenario instead of better scenario. We wind up at the detail of the budgetary, SI loss. Of course, SI is not only loss. This loss is only for people for reference and estimation. There are, the ILD, the crosstalk, the ERL, everything, the impedance values, everything matters. Every little bit matters in the 112G application, and Gen 6 application, right? For SI, it's not a simple solution. We did the layout, and we come out to this empirical value that. If we need because the LR, in the spec is 28 in IEEE, right? Also OIF. So, however, each IP vendor, they have a little bit headroom to let us, have a little bit stretch dB from ball to ball. So we give the reference guidance to 30 dB right here for both LR capable SerDes on both sides. From OEM to OEM is so-called scale up. Then we give 8 dB on the OEM. We give 12 up to 14 dB to UBB. Then the OEM RX will be another 8 dB, right? So from the expansion card to the OEM, which is scale out, right? If we remember the topology that it's going to the expansion card through the OD connector all the way to the retimer on the board. Right, so the retimer, after retimer will be another VSR budget. That's not a focus here today because that one is really short. Routing difficulty is the crosstalk and ILD, not the loss dominant, challenge. Here we talk about the loss dominant challenge here. So we'll give a 6 dB on the expansion card, include the connector and connector footprint. We give a UBB up to 18 dB. We give OEM TXRX 8 dB, which is aligned with our scale up. So if you can go to next slide. We did a scale for the scale up. We did the routing, and this one we actually have the manufactured the test coupon back in our lab. We did a measurement, however. We don't think that's a right time to share the measurement at this stage. We should only share the full wave post layout simulation. Again, the simulation is pretty good, aligned with the measurement results. Here, what we did is we routed the longest traces on the UBB as well as on the OEM, right? So the OEM, instead of using the actual ping map, definition, what we did is we actually did a 2.4 millimeter connector routing to mimic, the longest trace of the OEM was 8 dB on the OEM itself, right? Otherwise, we don't have a coaxial point to perform the VNA measurements. Then we actually did a post layout simulation on this one for SI, include all the crosstalk and the longest insertion loss. If we can go to next slides, Son. We quantify with the IEEE 802.3.CK COM, the latest version of COM contributed by the Richard. Then there are two cases. Basically, case one, assume there is a short, package loss in the chip package loss. Case two is assume there are 30 millimeter package loss, and wind up that the longest traces in the post layout simulation that we can pass the COM for the standard was the crosstalk introduced, which is a good sign. However, like someone just mentioned that the measurement will be more accurate, right? We do have a measurement result. We did pass the COM. The only reason is the measurement result has some, it needs some internal approval to demonstrate in a broader audience. So we haven't put into the OCP demonstration, right? So that's a scale, up study going to the scale out. That we will have a GPU or OEM ASIC all the way to the PHY retimer. After PHY retimer, again, you can terminate as QDD or OSFP 800G in a front pluggable. That's not our focus today. Our focus is from LR, from the LR retimer all the way to the ASIC. This one we did also did the layout by leveraging the engineering effort from 4 participants, which are the 4 major connector participants in the market. Did on the OD connector, as well as their routing was our standard stack up on the expansion card. Their routing to the one of the major SerDes IP vendor on the retimer side. We terminated in the actual ball map, did the layout and did the post layout simulation. Into the next slide, so is our demonstration on the S parameter itself. The 4 lines demonstrated here are the 4, participants. I haven't mentioned the name here. Just cover the names, but overall, from end-to-end perspective, there are good result. There are bad result. There are better crosstalk, there are worse crosstalk. This crosstalk is only have the not only, but this crosstalk is power sum result, because that the via in the via region that crosstalk may dominate. However, we treated using the more advanced technology such as the via Inpired, also the blind via, all those fancy technology. And we, whenever we have space, we put the additional ground shielding via to shield the crosstalk. Then our crosstalk is very, very good in the post layout simulation. However, you can see the insertion loss after 50 gigahertz, you have some different discrepancies. Some of them have a worse cutoff. Some of them have a pretty good linearity all the way to 60 gigahertz, right? That's dominant by the OD connector that we use from the 4 different participants, right? So different board-to-board connector, orthogonal connector have a different cutoff frequency performance based on their design. However, if we go to next slides, which is the detail of the COM analysis results, again, we're leveraging using the IEEE 802.3.ck COM code with the LR, assumption that we put a couple of figure of merit here from the different connector vendors results. Except the participant D, everyone else can route it out with 4 high-speed routing layers on the expansion card. The routing length, the actual routing length is in between 3 to 4 inches. This is on the expansion card. Then we cascade with the model on the UBB, because the scale out is from OEM all the way to the expansion card, right? We cascade it together and run the COM, and all of them pass the 3 dB result. However, there are two connector vendors have a better result. B and C, they have better result. They can achieve 6 or 5 dB. Then for ERL, obviously connector vendor C's result, cascaded channel result is the best. They can be a 16 dB for ERL. For form ILD, FOM, figure of merit insertion loss distortion, which is try to test the linearity of your STD21, that of course the C has the best results. So again, these are based on the full wave simulation. It will have some discrepancy compared with the final measurement result, which we are moving there. Eventually, we want to do the final measurement result and do the COM qualification again. Also, we want a SerDes IP vendor to do more assessment on the passive channel with their package model, with their SerDes capability, whether we can reach 1E-5 BER, prefect BER as our target, right? That's it for my part. So I will just please take it away.
All right, I think that's our presentation for today. All right, John, back to you.
All right. Next, we have John Norton NVIDIA with their HGX. John, do you want to start sharing? All right, we see your screen. Go ahead.
All right, there we go. Sorry, it took me a second to get off mute. Let me go full screen here. Look good?
John, you may want to go slide 1.
Oh, sorry. All right, yeah, so I'm gonna go over NVIDIA's HGX contribution to OCP. So I'm gonna cover some of the high level points of the contribution, talk through a little bit of detail, and give everyone an idea for schedule on when they could expect a complete specification. For those of you who don't know me, I'm John Norton. I'm a mechanical engineer here at NVIDIA. All right, so quickly, I just want to define HGX, what that means for people. So basically, that is a baseboard assembly that's designed by NVIDIA. And this particular HGX assembly hosts 8 of the most recently announced Hopper-based SXM modules. So you can see a rendering of the volumetric there in the top corner, but basically what we want to contribute is the mechanical form factor. This would involve the max XYZ dimensions, all the detail that would be required to define a chassis around this baseboard. So that would be keep in, keep out volumes, mounting locations, the position of the PCB within the volumetric, those kind of details. We'll also specify, you can see across in the picture there, you can see across the back, we'll specify the location of the signal and power connectors, as well as guide pins. We'll also share the signal names, pinouts, respective voltages, connectivity of all the connectors coming out of the baseboard, as well as power and its respective voltages and capabilities. So that was just a high level view. So here in this slide, you can see a little bit of details. So this board is approximately 416 millimeters wide. It's about 500.
Sorry to interrupt, John. Do you mind to share the other screen? You can click on the screen to switch.
Oh,
Yeah,
sorry.
we're seeing your presenter.
Are you seeing the presenter mode?
Yes.
I'll just go to this. That's probably better.
Thank you.
Thanks. Sorry about that. Yeah, so now much easier for you to see, hopefully. 460 millimeters wide, 553 long, about 145 millimeters max height. So the 3D volumetric that's shown here in this image, that'll be shared as part of the contribution. And as I mentioned earlier, we'll also specify, where in that volumetric the top of the PCB surfaces, as that's your primary datum for mating the connectors. Okay, so a little bit more detail here. So as I mentioned, you see in the center graphic, this baseboard hosts 7 GPU modules. You can see the connectors designated across the side. So there's power, high-speed signals management, and all of those will be specified with their position and respective pinouts and locations. We'll also specify the mounting locations where we provide SMT fasteners so that the baseboard can be mounted into a tray. If I go to next slide, I'll just at a high level talk about the connectivity here. So the baseboard has 8 by 16 PCIe Gen 5 connections, as well as additional PCIe connections, Gen 4 and Gen 2 respectively, as you see here. For management, we also provide a USB and I2C plus GPIO signals. and we have options on DC power input. We use AirMax and PowerMax for DC power input through the midplane. That would be mated to the spaceport, but we also provide RadSaw cable connections. Those aren't shown here in this model, but those will be detailed as needed in the contribution. The baseboard is designed to operate 48 to 54 volt nominal. And again, this was just a high level overview of what we intend to contribute. We're still working through all the details of that contribution, going through reviews, approvals, et cetera, but we wanted to introduce it here in this forum and give folks an opportunity to ask questions. And we're targeting the week of May 9th to complete this contribution. All right. And that was all the detail I had. I'm happy to answer any questions that folks might have.
Hey, John, this is Paul. I had a quick question.
Yeah.
Is there, it looks like you're in the keep out, it's room for a heat sink. Is there any keep out egress for like a quick disconnect and a cold plate for liquid cooling?
We are not specifying that in this contribution. There is, as you can see, certainly I'm sure there's room for somebody to go design something like that, but that's not something we're specifying.
All right, I appreciate it.
Mm-hmm.
Hey,
Yeah.
John, regarding the form factor contribution, would it include the pin out of the connectors?
Yes, definitely. We'll include the pinout and signal names and everything needed for interoperability into a midplane. That would include, everything that goes along with that. It's quite a few signals, so I didn't really want to just drop a slide on here showing a pin map, but yeah, that'll be included.
All right, thank you, John. Any other questions for NVIDIA? All right, before we go on to the inflammate success story, I'm going to go back a little bit. Questions for Song and Bitchin that were in the chat that we missed. There's a question from JP. What components have used PCI 6 in OAM? What's the maximum length for passive? Copper on QSFP-DD. That's something you want to talk to here or just answer in chat?
Yeah, the answer in the chat, right? I think the Gen 6 is going to be for the next gen OAM. Right now, all what we have right now is a Gen 5, but we on the spec itself, right? We want to be ready from the SI perspective. Mm-hmm.
Okay, yeah, I see that. And also another question in chat that the 12 volt is removed from the OAM 2.0. Yeah,
I think it because if you look at the trend of the OAM, the usage, right? I think it's going to be high power. So 12 volt is going to be very low efficient, right? That's why that we are moving to the higher voltage.
Right. Okay. And then there was a question on enlarging the SXM format to make it more compatible with OAM or NVIDIA in chat.
I'm sorry, I missed the first half of that question. Could you repeat that?
There's a question in chat. Are you considering to enlarge the SXM format to be more compatible with OAM in your next generation modules?
I'll have to follow my sword on that one. I don't know specifically whether SXMs are larger or smaller than the current proposed OAM. I saw the form factor a little earlier. I'm not sure exactly how they align. I see the follow-up here on OAM 2.0. Is there a plan?
I think the question is to NVIDIA is the SSM is going to increase the form factor to be more compatible with OAM. The OAM is slightly bigger than the SSM.
Yeah, I think our contribution is the HGX form factor as a whole, and not include it doesn't include an intent to align SXM and OAM.
Okay. Any final questions for the OAI or NVIDIA before we move to the success story? All right. Next up, we have Peter Chen on an Inflame Inspire success story. Let me stop sharing. And Peter, you can start sharing now.
Okay, can you hear me?
Yes, we can hear you.
Okay. Can you see my screen?
Yes, we see it. You're good.
Oh, okay. So good morning, everyone. This is Peter from the Inflame. So it's very glad to share the storage under the OAI and also our journey in the OCP. So I will cover 5 sessions. First will be who is Inflame and what we're doing under the OAI committees. Also the Inflames, the OAA product family. And then I will introduce our liquid cooling OAI systems. Also, based on these systems, we create a training cluster. And the last session will be our soft stack. So Inflame actually a startup in Shanghai, which have been founded in 2018 March. But actually we joined the OCP in the very beginning. So in 2019 July, we joined the OA group, and also quickly we released our first generation OA modules and around 2019 December, and also we quickly to development our second generation OA modules about less than 2 years later. And actually as a startup company, it's very grateful here to open the door to us for the OCP, and also we participate this the community or not almost every year here in China. So we joined the China Day from 2019 and 2020 and also 2021. So the OAA product family. So this is our first OAA product. We call it Cloudblazer T11. So this is OA. It's the OA spec version 1.0 compatible, and actually it's the first OA module in China. And the TDP is about 300 watt. Currently, this module actually is in production. Our next generations, the OA is about 400 watts, and it's about going to mass production later this Q3. And this OA module is the spec version 1.1 compatible. So this model actually both supports the air cooled and liquid cooling both. This is the detailed spec here. And actually besides the OAA, we also create several like physical level test solution here. You kind of develop a lot of those test features here to like measurement the S parameters for both the UBB and the OAI, and which can be easily to evaluate the channel loss budget and also check the OA and the SerDes technologies and debug the SerDes issues. Like this one also can debug some PCIe issues, and it can improve the UBB and OA SerDes for in design. We also plan to contribute this in the in OAI. My colleagues next time we can share this. Yeah. The liquid cooled OA systems. So just mentioned, so the Infinite didn't have a longer history here. Actually, it's about 4 years. But while we choose the liquid cooling, I guess there have few reasons here. First is a higher TDP, because the kind of the chip and also the OAA itself have the higher compute density, which means more power. Like T21, we have the 400 watts. Also, the next H100 have the even 700 watts. The air cooled cannot handle those such much power, and also the liquid cooling can offer the better TCO. And I guess especially in China right now, the government have very aggressive the goal for the carbon peak and carbon neutralities. And I guess from last year, the government here is want to have the national computing network to synergy the East and the West. I guess most people know, like here, we have a large population in East, which means the data is mostly located here. But in the West, we have a lot of the free cooling there. So it's kind of to synergy this. We plan to build a lot of the national computing network in the West. And also, actually, a few projects, the government have their very critical PoE's limit. So which means if you cannot meet this PoE limit, you cannot implement your system there. So given those reasons, we chose the liquid cooling for our first generation the system product. So this is the inflamed UBB and the system topologies. This picture is the UBB. So you can see here we have dock 8 OA modules, and this UBB is spec to version 1.0 compatible. And this is kind of the air cooled. They have this 8 OA module here. And this is our system topology here. We have 2 CPUs, 2 PCI switch, and 8 OEM here, and including both the PCI link, and also we have the inflate defined, we call DCU near, to connect this 8 module together, which can form 3 rings. And also we use the IB or Rocket to scale out. This is the OA-based OA system, OAI systems. So this system actually is they have a 4U chassis, have 2 CPUs, and you can have the 8 both like T11 and T21. And the UBB is the spec version 1.0. And we use the cold plate liquid cooling. You can see this is the nectar cold and hot pipe here. Let's look like inside for more details for these systems. So this is the UBB tray, and it have the 8 OAM here, and it can call about the capacity up to 3,200 watts. And so we also have the QuickLogic here, the connectors, and from the front to the rear, actually the manifold is here, and this is for the CPU, and this is for the OEM. Yeah, to calling those. So with these systems, we also built a large training cluster. So this first step is the system rack. The rack is 42U, and this is the prototype here. You can see we have the three the OAI systems, and also have one CDU. And this is a rear view. You can see the pipe, all those things here. And we can support up to 8 to 10 compute nodes in one rack. And the rack power can up to 63 kilowatt. Yeah. So this is the training clusters. We have the tower here and have the CDOs and all those racks here. And actually we have a project which have up to 1,280 OEM and 160 servers, and which is actually the 20 racks. And we both use this coplated liquid cooling, and the rack power also 1 for 1 rack up to 63. This is the diagram for this matrix. We have the compute cluster here. As I just mentioned, we have the 20 rack here, and we use the GCU near for the scale up inside the server, and we use the RDMA network for the scale out. And this is storage, the cluster. We kind of use like the high LPS, the storage cluster like the DDN. And this is a management cluster. And for the network, we have the compute and storage network, and in-band management and out-band management. It uses a factory network to connect all those compute cluster, storage cluster, and management cluster together. Besides this hardware, the systems notion, we also have we call the cloud-based station for all the very comprehensive software stack. It's from the hardware platform to the system firmware and also the OS kernel driver, and we have the path to offer all the service, and also have the SDK framework and SAS different layer here, and also to support different kind of modules, and then for the different AI scenario, and also have the AI ops to manage all the equipment here. Yeah, I guess that's all for my sharing today, and yeah, thanks for for Whitney and Song and also the OI friends who invite me to share our product here, and also I guess for the InFrame, this is kind of a very small steps in the last 3 years. Hopefully in our next phase, actually we are planning to our development our 3rd generation OAI and also the UBB, and hopefully we can have more collaboration with OAI, and also we can contribute in this community also. Yeah.
Thank you, Peter.
Yeah.
Thank you, Peter. Anybody have any questions or follow-up for Peter or InFlame? All right. Next up, we have Alan doing a HPC subproject update. Alan, you ready to present?
Yeah. Is that coming up? Can you see that?
Yes.
Okay. Okay, is it gone full screen?
Yeah, it has.
Okay.
You're good.
Perfect. Okay, hi everybody. Yeah, my name's Alan Cantle, and I'm presenting on the OCP High Performance Computing subproject. I'm going to give you an update. So if you're new to this and you're not familiar, I recommend you also go to the Introduction to OCP HPC at that YouTube link, and that will give you a lot more detail than I'm going to go into today. But first, I'd like to start to take a step back as to what we've been quite radical in what we're doing in OCP HPC, and it's really driven with this energy-centric computing perspective in mind. And so I wanted to give you a better understanding of some of the conclusions we've come to in terms of how to proceed forward. So energy-centric computing, really, we all know that data movement consumes the most energy in computing, and it really provides zero utility. You obviously want the computer, the processors to do the work, not spend time moving data. So over the years, I've come to these three guiding principles. One, minimize power when the data is idle. Two, don't move the data unless you absolutely have to. And when data has to move it as efficiently as possible. And our guiding light is the value is in the data, and the processor cores can often be effectively free, so distribute them freely. A good success story is mobile phones, everybody knows. That's very application specific, seriously constrained real estate, and the goal is ultimate performance per watt, so that you can fit within the very tiny 1 watt power envelope. The way they have achieved this, and we all know what Apple have done, they've got domain specific on silicon. So that's many heterogeneous processors that are very efficient at their particular function. And they've done that very specifically for all the phone's needs. And it's an amazing feat. But basically, this is the best you can do. This is the best optimization in a monolithic die. And they even have very ultra low power interfaces to the neighboring components, the very few neighboring components. So that's what you can do when you've got something in a mobile world and you've got the volumes to drive it. But we're taking a leaf out of that book, heterogeneous domain specific architectures, and we're doing domain specific on package with chiplets. The high bandwidth memory is probably the most successful integration of chiplets into a package with processors, but everybody's looking towards multiple heterogeneous processors in a similar way to the way Apple have done. But these are done at the chiplet level, so you can mix and match that for your particular application for the most efficient implementation. You'll be hearing from OCP's ODSA shortly. And they're focusing on chiplet standardization. Very excellent working group. I thoroughly recommend them. So, but this does give you a very constrained physical composability. You know, there's quite an expensive packaging job by the experts, and the ultimate goal is really the best performance that you can achieve. But your performance is really constrained by power ultimately, and as was just said in the previous presentation, NVIDIA, I think, have the record with their latest H100 is in the 700 watt region, and we've been talking about trying to get to a kilowatt region in these modules. So that's the constraint of as far as you can really take it. But what about system level energy-centric computing approach? Well, I don't think that the idea here is we believe there are better ways to do this. So, but what we see is supercomputers of today. The top left is the Summit machine from 2018, and the bottom left is the Frontier machine just being installed now. And they're heterogeneous in a node, and with a mix of GPUs in both of these cases and a couple of CPUs. So they're very similar architectures. Again, we're going heterogeneous. I was going to say proprietary. We've got the HGX from NVIDIA. I've just heard that they're opening that up, so that's great news. Another good example is Google's TPU for AI machine learning applications. Very, very, very custom. And you've got this more general purpose, this desire for us to have software composability, so we can pick the pieces that we need and compose them quickly into a particular application, but in a disaggregated rack. But is that really energy efficient? you've got to move that data an awful long way. And so I think there are some fundamental flaws in this thinking. So this is what's driven our thinking on this, of making things much more flexible. So I tried to say, how can we see the energy that's being consumed by the I/O? And so I've tried to do this, and I'll take any input to improve it. But we talk about moving data in energy terms in picojoules per bit. So for example, a terabit per second, you just multiply it at a picojoule per bit I/O would give you 1 watt of power consumption. So that's just the basic equation. So I've drawn this diagram. You can see that we've got data movement in energy is shown in red. So all of the I/Os that are going on, obviously things like NICs and PCI switches often are just I/O handlers. But I want to emphasize a few specific pieces here. First of all, the HBM, you can see this chiplet connection is 0.5 picojoule per bit, compared to a standard interconnect is in the region of 5 to 10. So there's a 10x order of magnitude gain by bringing the memory on package. But not only that, the actual memory itself in the 3D stack is only 4 picojoules per bit for this HBM stack, compared to a 34 picojoule per bit for a memory DIMM, a large memory DIMM, albeit at 256 gigabytes against the 16 gigabyte HBM. Optical modules, they're typically in the 10 to 20 picojoule per bit. So obviously, it still makes sense to stay in the electrical domain until you exceed that by adding repeaters, etc. So this is just where we're at today. And finally, in the SSDs, this was a little bit of an interesting one for me. You think that if the data's idle, you'll burn no power, but actually the controllers in these SSDs do burn quite a bit of power if they're on the ready to go, and their idle power is similar to DRAM. And more interestingly is when you do access them, they actually do consume more power than your DRAM. So that's an interesting thing to bear in mind. But suddenly it allows you to think about things from an energy perspective when you start to draw block diagrams like this. So hopefully, I want to refine this more, and I'll take any input from people. So let's take a look at the frontier node from an I/O energy perspective. Again, it's a fixed heterogeneous node topology. So what we mean by that is you've got the CPU and you've got a dedicated set of wiring to the 4 GPUs with Infinity Fabric. And that's the wiring diagram on the right there. And the CPU has its 8 memory channels. But and you can see there's two Infinity Fabric links from the CPU to each GPU. But what if your application, if you analyze your application, you said, oh, I need the bandwidth of 6 XGMI links, Infinity Fabric links between my CPU and one of the GPUs. Well, sure enough, you can do this with this architecture, but you're going to have to route 4 of the lanes through 2 of the other 250X GPUs. And that's a very expensive, wasted energy way of getting that, versus being able to directly connect 6 lanes from the CPU to the GPU. And that would be much more energy specific, energy saving. Also, what if your application needs deeper and more memory bandwidth? You know, HBM's great bandwidth, but not very deep. DDR is very deep, but not very good bandwidth. But what if you do need more? Well, unfortunately, that's decisions made inside the at fabrication time of the processor. The designer decides how many local memory channels and how much I/O they have. So OCP HPC, we've got a system level and energy-centric architecture vision. So what I'm going to show here is an abstract view of where we would love to take the industry, but it needs a lot of collaboration. We'd like to tightly couple compute with all and any memory types in a pluggable 3D fashion. So we're taking this heterogeneous, this compression of the technology to the system level, not just silicon and packaging. And we'd start with, in the middle, we've got many terabytes of memory. It could be non-volatile, persistent, or file system storage memory. And you've got a high performance processor still connected, the big heavy lifting processors. But we want the lowest picojoules per bit, lowest power energy between those two, and the lowest latency, and as high a bandwidth as you can from a pluggable interface. Inside each of these memory devices, you would have distributed tiny little embedded processors. They can actually deal with some compute and avoid moving the data across these more power-hungry interfaces. So it's you're distributing the computing there. And then we want to efficiently share that processor's near memory with other processors in your system when you come to a big system. So we have a high bandwidth memory pooling data plane fabric. And this is the point where we would ideally hand off to silicon photonics. We'd have a shared memory buffer through a shared memory buffer interface. So there's 2 ports on the memory, one to the big high performance processor and one to the distribution fabric. It's not a processor interface. So this is a vision of where we'd like to get to. But obviously there's a lot of things that need to change here in the industry for this to happen. But we can still build the same architectural approach to take our first step in the system level architecture towards this vision. And that's what we're doing in OCP with our high performance compute module called the HPCM. It's inspired by the OAM module, and it leverages EDSFF media technology. So the key thing is it's modular, flexible, and composable. And it's protocol agnostic at the module level. So we can run anybody's bus across these modules. We don't want to pick a winner on protocol technologies. But the key thing is we can mix and match memory, storage, and I/O with all of the interconnect. Obviously, it will depend on whether a processor can support it or not. An FPGA, for instance, is a Swiss Army knife, so you can switch between different interfaces. And you would choose that mix depending on your application need for the best performance at the best power point. I'm just going to flash this up so you see the physical look of the module. Again, go back to my general overview presentation to get a better understanding of this. But on the left, you can see it's like an OAM module with a powerful processor on the top, but we've replaced the mezzanine connector with module connectors and cable connectors. And on the right, we've given an example of E3 modules, NIC 3.0 modules, and cables plugged into the module. Again, I stress for you to watch the main presentation to get a better understanding of this. And if you look at this, it looks very much like the block diagram. I believe we can get to those energy targets with this physical architecture. Okay, so what are we actually doing in the OCP HPC update? Well, we wanted to choose an application, and we found out really that AI. This was one application that needs low latency high memory bandwidth, and a tremendous amount of capacity that HBM can't give it, and DDR can't give the bandwidth. And Berkeley Rise Lab have shown these numbers. That's a bunch of graphs showing basically this need. So we said, well, okay, it looks like a good application that we could focus on. But at the same time,
Alan, just time check. You got another 2 or 3 minutes. I don't know.
Yeah, I've got a couple of slides. That should be it. Okay. But we want to do we wanted to replicate an HPC node. Can we actually rebuild an HPC node as well with this architecture? So we looked at a Summit machine. That's made up, as you can see there, with 6 NVIDIA GPUs and 2 IBM Power 9s. We wanted to put it in the OAI chassis. So we'd like to house this in the OAI chassis as one implementation. And so we would design two HPCM modules, one for the IBM Power 10 and one for Xilinx Versal. And we're working in collaboration with AMD and IBM on these modules. And we would attach a lot of OMI memory to the FPGA modules. So we've got up to 38 terabytes. This is where it's different. It's the same architecture, but it's much more memory, and it can go at 5.8 terabytes per second. So this is of interest to the AI community. Just to look at the modules are simply the processor chip and the interconnect. And obviously you've got the power supplies and some sideband, which I'll touch on. IBM's is very specific, so the modules you plug in need to match IBM's needs. On the FPGA, it's the same module. It's the FPGA connected to the same types of connectors, but you've got more configurability in the I/O because they're programmable, software programmable I/O. And so we're building these 2 modules. That's our starting point, is trying to bring these 2 modules to reality. And finally, a critical part of our project here is the board management controller and sideband management. There's an awful lot of that in there, and we want these modules to boot independently, but we also want them to be designed to integrate in with the DCSCM security module infrastructure that will be housed in the OAI chassis. And so here, Lattice are contributing some of the serial tunneling protocols that will allow for an efficient implementation in the design. And they're helping us with this. So in closing, that's what we're up to. We are a sub-project where we're focused on creating an energy-centric computing architecture that is open, modular, flexible, and composable. And my call to action is, we're an unfunded working group. We're looking for volunteers, anybody that can bring some ideas and help to get us bring these modules to market or to prototype would be great. And we're also looking for funding sources to help accelerate the progress. There's my contact details below and also a few links if you want to find out some more information. So thank you very much.
Thank you, Alan. Anybody have any questions for Alan? All right. Well, thank you very much, Alan.
Thanks.
Next up, we have Bappy with the ODSA, and we've got a bunch of lightning talks here. So there'll be a lot of speakers coming through. You want me to put up the schedule, Bappy, or you just want to start sharing?
Actually, the schedule would be good. I think we're suffering from a speaker shortage. Would you mind putting that up?
Yep.
Yeah, so I apologize, but I'm going to do a quick roll call to see who's online. I guess they can't speak up. I see Ketan.
Yeah, anybody can unmute themselves. So anybody who's on this BOW
Ketan's online.
Stuff, unmute and say hi.
Ketan Ilad, you online? Kash, I see you. Gary from NXP, you online? JP? Okay, we might have a seriously short session. Mao from QuickLogic. I have a whole bunch of slides, but no speakers. Jim Finnegan. I could have sworn I saw Jim on the list. And
hello, can you hear me now?
Yep. Who's that?
Oh, thank you.
Who is that speaking?
Normally, I put my SSD picture, to be honest with you, but I am joining the OCP online thingy. So I don't want to put the Samsung SSD there. So let me just change that picture.
Okay. I think I'm wrong.
Hey, Poppy.
Yeah.
Alad is going to join in a second.
Okay.
Alad is going to join in a second too.
Okay.
As well.
And Wensin. Okay. I think we've got a quorum. We can go.
Jim Finnegan is here, Bobby. I see him.
Yeah, I saw Jim too. Thank you. Yep. I see Jim. We've got a quorum. We will get the others in when they join. So the order may be massacred a bit, but that's life. Okay, I can share my screen now.
Okay.
I'm going to we're behind schedule, so I apologize up front. All right. Hey, everyone. My name is Bapi Vinakota. I have the honor of leading the ODSA subproject, and we're really excited because today we're trying to do something unusual, give you an update for the project in terms of what's happening in the community, in terms of what's happening in member companies, making products, prototypes, IP, tools around the ODSA. We're a subproject that aims to, we're built from the ground up to address die disaggregation and to enable chiplet-based product development. And there are a couple of models for chiplet-based products, and we can fairly confidently say we're the best in class for die disaggregation and IP reuse. And one of the things we're really proud of is that we're non-prescriptive. We hit the widest range of price points and applications, and we're truly open. In fact, I'm fairly confident you'll see in a couple of presentations things we could actually be doing better. So we're incredibly open. Players of any size. Many of our leaders are actually startups. We've got leaders from big companies, startups, and people can join in at any time. And newer contributors have become active contributors fairly quickly. We have a really wide range of participants in every stage of the semiconductor fab chain. We've been in existence as a project for about 3 years, and in that period, we've had many companies, big and small, join us. ranging all the way from IP vendors, tool vendors, semi vendors, all the way through tools, the manufacturing line, the companies in the manufacturing line, to systems vendors and hyperscalers. So I'm sort of zipping through. I'm happy to leave these slides online. What really our serious strength is our community. We have an incredible collection of workstream leaders who have really produced some fairly significant output that is in pretty rapid times become an industry standard. Kenneth Ma led the effort to release the first specification produced by the ODSA. Shahab has led the effort to produce a cross-PHY spreadsheet that has become the objective standard for comparing die-to-die PHYs in the industry. Ravi Agrawal led a business workstream effort that, in my mind, I believe broke the record for a single topic workshop in terms of number of registrants. We had more than 600 people registering. JP has produced a prototype, and you'll hear more about them. We produced a board prototype completely in the open, an astonishingly massive challenge. DJ has represented the voice of the end user. Elad's come in and taken a crack at leading the bunch of wires effort and really bringing it down to a draft specification, monumental effort. David Rajkov has really, and Jawad have worked on putting together a design flow for chiplets with lots of participants from EDA vendors and leaders in this space. So we made tremendous progress in my mind towards enabling the commercial production of chiplet-based products, especially those with internally sourced chiplets with open interfaces. I'm not going to go through this. I will be happy to follow up with you on this in a separate talk in our weekly meetings. As a group, we meet weekly on Fridays at 8 a.m. Pacific, and each of these streams meets weekly as well. And you can find meeting information at the ODSA wiki. So in terms of 2022 plans, we really are very excited by the arrival of the UCIe, because we as a group are very excited by any activity that produces a new open interface. We want to collaborate. We've had a strong track record of collaborating with other open organizations like the IEEE and the CHIPS Alliance. And some cases there's some overlap, and some cases our work is entirely complementary. We'd really like to continue the great work we're doing in 2022. But the most exciting thing about 2022 is that products are in flight, and that's what our system is about. Our session is about. We might have run into some teething problems where we have slides for all the speakers, but not the speakers themselves. And I'm going to try to round them up in the next 30 minutes. But if we don't, we will bring them back. What we've done is done some quick lightning talks for people for each of these things. And we will try and see if we can get them actually on for longer talks, if you like these, at our weekly Friday session. Okay, with that, hopefully, John, I've reclaimed some of the time we have. With that, I think since Kash is on and Rishi is not on, I'm going to go to Kash for your talk. No, okay, is Ketan on?
Yes, I'm on.
Yeah, so I've organized this into about four groups. We have session one is on the Open HBI interface. Session two is on the bunch of wires interface. Session three is on prototyping, and session four is on commercial products, mini sessions. We're not going to take breaks, etc. All right, Ketan, it's all yours. Please tell me when to move the slide forward.
Yeah, thanks, Papi, and thanks everyone for joining, and appreciate the sponsorship here, all the sponsors for this talk. My name is Ketan. I'm at OpenFi, which is a sci-fi business unit. Let's go to the next slide. Okay, so how did we join this group? Essentially, let me say a few things about OpenFi. We are a custom silicon solution provider with a differentiated IP. What it means is that we provide a custom solution for each of our customers. We have 350 plus tape outs done. If you guys know Open Silicon, which have designed the chips up to 5 nanometer and beyond. We provide the customized IP. Our customer have been asking, because of our background in interlaken and HBM. It's funny, Ellen just mentioned about HBM. We've been doing that for about 7-8 years on CoWoS packages for our customer. And I think those HBM connectivity, electrical perspective, and interlaken chip to chip is what brought us to ODSA. There was an early group started by Kenneth at Xilinx on OHBI, so that's what we joined and participated, and that's how we are at ODSA. You can see the group of company who started that effort, and the Open HBI was finalized in the December of last year. Next slide, please.
Oops.
So in terms of the ODSA, as I said, we support the 5, which is compatible to Open HPI version 1.0 spec, which has been already published. It runs at 8 gigabit per second. So we support that. In fact, our IOs are actually optimized to support the BOW draft that Papi mentioned earlier as well, including other PHYs. We have changed the termination and the driving circuit compatible to other specification as well. And then we can port it onto a BOW or other PHY based on the bump map and the package requirement. In terms of our current die-to-die subsystem as a PHY, talking multiple dies together, we support all the way up to 16 gigabit per second. In fact, that's a package and distance trade-off. We do less than 0.5 picojoule per bit, the normalized power that Alan explained, and about 3.2 terabits per millimeter using quad PHY slices. We do less than 5 nanosecond latency on the PHY, TX plus RX included. And then we support the advanced bump pitch, is about 55 micron bump pitch for the advanced packages. And the interesting thing is that this is all proven on silicon for us. We have, in fact, 2 silicon, 5 nanometer and 7 nanometer. On 7 nanometer, we actually are putting 2 dies back to back, talking to each other on advanced packages. So that's a great milestone for us. Our customers are happy to see that. More information is available on our website, which I listed here. Next slide, please. This is the link controller that goes on top of the PHY. So essentially, we support all different types of PHY, and we have an adaptation logic here as a framing layer that you can see connected to the PHY layer. This framing layer adapts to whatever type of PHY it is, be it an XSR PHY or BOW or OHPI PHY. And then we have our legacy interlaken functions morphed into die-to-die controller, which has support for the end-to-end error-free delivery, flow control, and the retransmission as well. So that's a full-fledged controller that supports various functions. People can modify that and suit their needs for latency and gate count. And finally, on the system side, we provide an AXI shim bridge, which you can connect to either your NOC. We have supported a cache coherent interfaces as well to some of our customers, and I have some examples on the next slide. This is our actual customers. So in the past, we have connected CPU chiplets for our customer. There is a Sci-Fi CPU core complex on both the sides. These are cache coherent, and they've been connected on a multiple die using our die-to-die technology. The bottom left, you can see a GPGPU chiplet. Customer has actually tried to disaggregate their large die, reticle limited die, which is now connecting multiple dies together using our die-to-die technology, of course, and you can see some HBMs there. And then on the bottom right, it's another type of disaggregation on IO chiplet that's very useful today. You guys can visit my talk.
Is this performance degradation only, or will it cause UECC, data loss, that kind of stuff?
I'll take some questions at the end. There is actually a header that goes into the packet itself. So there is some degradation
so
of
they will
5%.
see UECC. So that means they will see a data loss, right?
Yes, it's about 5% degradation.
Which is what they are using currently anyway, right?
Absolutely. Absolutely. So going on the bottom right, again, there's an IO chiplets, where customer has tried to disaggregate the main die from the IO die, and the IO die itself has PCIe and Ethernet stack on it. So essentially, you can disaggregate the long-range SerDes from your main technology die that allows you flexibility to support multiple IO. So as you can see, these are our actual customer chiplet examples. Feel free to reach out to me if you need more information. I have one more slide after this, and I should be done.
Oh, there you go.
So what is next? We believe that the customers which are requiring a connectivity to a specific CPU, GPU applications, there are so many. We have an alphabetic soup now in terms of connectivity. You can have UCIe, you have an NVLink, BOW, OHPI, and of course, people have a choice to connect XSRs. There are multiple PHY interfaces exist. Our intention as a custom silicon provider is to support all of them, including the customized IP. However, the customers which are requiring the heterogeneous die disaggregation that Alan mentioned earlier, the closed box system that already exists today, and we are supporting our customers already today for die disaggregation. So going forward, how does this all come together? I believe there'll be a huge amount of collaborations between the foundry and the IP silicon and the OSAT providers taking various types of chiplets. The one I took example earlier, which is CPU, IO, and heterogeneous chiplet to the next level of optimization. So this is where we are at ODSA. We are extremely excited because the group offers a lots of technical background to us and help us foster this technology. And thanks, Bapi and everybody for their effort that you're putting in. That's it. That's my last slide. I'm open to questions, or we can take questions offline.
All right, let's do questions offline or at the end of the session if we aggregate some time.
Absolutely.
That was wonderful. Thank you. I see Rishi's on. So Rishi, I'm going to bring yours up.
Yes, yes, please.
If I can actually open the deck. 1 second. All right.
First of all, good morning to everybody. Good afternoon and good evening for folks who are joining remotely. This is Rishi Chuk from Cadence Design Systems. And I would like to thank Bapi and the entire OCP ODSA forum to give Cadence the opportunity to represent our proposal and offerings over here. With that, I will kick off my presentation. So we have seen that chiplets have been predominantly being deployed on various class of heterogeneous systems. And primarily what we see over here is a reuse of design. And we are basically looking at drivers which influence chiplets to be used as a primary SoC interconnects. We have seen this deployed in processor. We have seen this being deployed in memory and storage SoCs, and we have also seen it deployed in connectivity. And clearly these applications have very unique requirements, or these verticals have very unique requirements in terms of speeds and feeds, in terms of the process nodes, in terms of the bandwidth, what they care about, and the characteristics of the SoC by itself. For example, processors basically look at low power, lower latency, and they need not look at the high throughput aspect of it. They look at emerging process nodes because they stack a lot of CPU cores inside it. On the memory side, basically folks look at interconnects in terms of lower latency, but also lower power. And there is a huge amount of storage being transferred from one die to the other die in terms of packet buffering. So the beachfront density or the overall throughput of the design becomes critical. Also in terms of storage, when we talk about not only latency, but also the bit error rates. You don't want to lose data. So that's another aspect of the storage-based stuff. Connectivity is more challenging as folks start discussing about 25 terabits, 50 terabits of switch fabric. And over there, the radical size of the die is a bottleneck, and people start distributing the features of the fabric by itself by keeping the packet processing within the main core die and the layer 1, layer 2 on the chiplet side of stuff. So it gives them that flexibility. And also another aspect of the fabric or connectivity is the OE aspect of it, which is the optical engine. People are trying to do basically co-optics on the die by itself, and they don't want to use the optical module for the beachfront density requirements or the bandwidth requirements. So silicon photonics optical engine also becomes part of the chiplet family. Next slide, please. So clearly, as other presenters have presented over here, where we look at the investments into chiplet-based SoCs, there is no one fit for all type of a solution. And that's why we are over here, where we look at what are the most critical metrics where any SoC design looks at a chiplet-based design for. They look at the yield and the cost aspect of it. They look at the bandwidth and the beachfront density aspect of it. And then the architects, they look at whether they should use an NRZ or a PAM4, what are the power requirements, what are the latency requirements, and how does the SoC fit into this particular interconnect family. Within this, at a broad level, then there is verticals for parallel interface. We look at OHBI, AIB, which was eminent from Intel previously to these forums. Then we look at NRZ interfaces, very much similar to what we have in Bo and what Cadence offers as well in terms of the Ultralink PHY. And then we have parallel interface, which is governed by bodies like OIF, where optical engines come into play, where we have the XSR. So clearly you can see there is deviation, and of course now there is even UCIe, there is NVLink, and then we have our own homegrown OHBI and Bo. Bottom line, all of these particular aspects of chiplet-based PHY or chiplet-based architectures are not driven because people like you and me love to do different variants in life. It is driven because of these parameters which are governed by the SoC requirements. Every specific SoC, as they architected or their use model, have these unique requirements, and we are trying to basically set as a standardized baseline as to what will fit best to the industry. And Cadence has been in this play for the past, I would say, more than 4 years, working very closely with the Open Compute Forum and especially on the ODSA, contributing not only on the standard side, but also enabling our customers. If you look at the deployments and the landscape, this is no news to any one of us who's on this forum. We have seen how legacy processors. Yes.
I'm terribly sorry, but another minute or so, or about.
Yeah, sure. The legacy processors, which were there in the older generations, have changed into workload optimized processors. The memory and storage components, which we are seeing today in the modern design, have changed into fragmented or disaggregated components, which are sitting on the die.
That's good, though. I'm just going to surprise. It's very quick.
Yeah.
Sounds like we're going to have.
Would you mind saving
by the middle of next month?
Okay, thank you.
Okay. Sorry, am I going too quick? Or?
No, you're all good. You're all good.
Okay.
Unintended interruption.
Okay, sorry. Okay. So as you can see that all of these examples which I've highlighted over here are something which people are doing today, which is in the public domain. And people can see that folks, as they start designing these stuff, they are looking into optimizing of their design and using chiplets in some form or the other. So if you go into the next slide. So on the chiplet landscape, even on the connectivity side, what Cadence does, what Cadence brings on the table over here is basically, we get basically a set of requirements. We convert these requirements into an SoC architectural proposal using our technology, our PHYs, based on what the SoC needs. These PHYs are basically adhering to the OCP standards of ODSA, and also we are basically proliferating into different segments of chiplet as a design by itself. Not only from the PHY, but an end-to-end chiplet solution where we get a full, I would say, design of the chiplet-based die by itself. A whole complete design coming from Cadence, where customers can basically then take this design and start doing basically silicon manufacturing of that design. We work with our customers closely. We provide them with different proposals, and we have basically the PHY, the layer 1, layer 2, the controllers associated with it, and you get basically the whole design in terms of optimized latency, optimized performance, and the best-in-class PPA, because we are not just looking at the PHY or the controller side of things, but we are looking at the full data flow stack of it.
And we're out of time, so do you mind if I push you to the last slide?
Yeah, just push to the last slide, yes. So what I would like to highlight over here from a Cadence and ODSA point of view, we have been contributing and carving the path in the industry towards chiplet-based design. Today, we do have the full 3D tool support, working on close-up partnership with OCP as well as with multiple foundries. We have these IPs and these solutions in various nodes, in various foundry houses.
Okay. Yeah.
And we have seen successful deployment. Go ahead. Yeah.
No, it's not a question. It's an interruption again.
Okay. So, and on the last note, I would like to say, basically, you have seen the PPAs of these IPs, what we have today. We have 3 of them today, and we are working to enable much more, and these are available in various process nodes.
All right. Thank you.
Okay. Thanks.
Thanks so much. And our next speaker is Elad.
Hi, everyone. Okay, do you mind going full screen, Bob? Thank you. Yeah, so my name is Elad Alan. I'm one of the co-founders and CEO at Blue Cheetah Analog Design. And I'll tell you a little bit about some of the bunch of wires interface solutions that we'll be providing. So first, just a little bit about why we've been involved in ODSA. Generally, we support any of the chiplet die-to-die solutions that foster the broadest possible use cases and applications. I think you've heard a lot about this already. But I did want to mention that ODSA BOW is really the first standard, particularly the first open standard, that supports both the organic laminate packages and packaging independent PHY definition. So we've been very heavily involved in the BOW PHY specification for a little over a year now. We sort of started out in both the PHY and the test chip working meetings, and then we've been sort of involved in a number of the others as well. We're actually one of the 2 companies that's providing test chips to demonstrate BOW PHY interoperability. And I personally have been technically leading the BOW PHY working group, as well as heavily participating in the BOW link layer working groups with a lot of our contributions being mostly focused on the electrical specs and interoperability, but also just sort of generally trying to drive all the group towards what we believe will be the best solutions. Next slide, please. Yeah, so in terms of products that we are offering based on ODSA, we're offering a family of BOW-based die-to-die solutions. These cover either organic laminate or advanced packaging. As I said in the beginning, BOW is fully appropriate for both. Anywhere from about 55 to 130 micron bump pitches. From an energy per bit perspective, again, state-of-the-art performance here, so 0.3 to 0.5 picojoules per bit. Anywhere from 2 to 16 gigabits per second per line. Less than 1E-20 raw error rates, less than 2 nanoseconds latency, and up to about 25 millimeters reach on these organic laminate packages. Furthermore, there are indeed low latency link layer controller solutions that we offer that support die disaggregation of AMA buses. These are based on the link layer solutions that are being, the link layer specification that is also being developed in the working group. So we have a number of silicon tape outs in progress, both a 12 nanometer test chip, again, on organic laminate package, doing the 2-stack. So this one's at about 0.5 terabit per second per millimeter, or 9 terabits per second per millimeter squared of bandwidth density. This is done on, let's say, a medium end organic laminate, so 424. And this is the same test chip that will be used in the ODSA interoperability package test vehicle. We also have a number of 5 nanometer PHYs that are embedded into multiple of our customers' chiplets. That again, these tape outs are in progress right now as we speak. So if we go to the next slide. So in terms of what's next for us, obviously BOW is sort of on the cusp of being sort of formally approved and released. So we're very close there. There's also a lot of work being done on the link layer specification. We're targeting to get that out formally in summer 2022. We within Blue Cheetah are going to be taping out at least 3 more additional bunch of wires PHYs in various advanced FIFET processes by basically the end of Q1 of next year. And I personally, as well as members of my team, are planning to continue to provide technical leadership on future versions of the BOW specification, particularly to support higher data rates, to support some of the power management features, to ensure we can do proper compliance testing, to do sort of other additional features like redundancy, variable slice widths, and so on and so forth. So with that, I think I'll stop and give ourselves, so hopefully I caught up a little bit of time.
Oh, you did more than that. That's wonderful.
Yep.
Thank you.
Of course.
And Elad's has been absolutely fantastic as being the leader of the Bo work stream. So thank you.
Thanks so much, Bobby.
Next up is Kash from Etopus.
Hi, good morning, Bobby and everyone else. Just want to thank the folks that are sponsoring Open Compute and ODSA. I think we're new to this, but it's been very good to us. We're excited to join and showcase a little bit of what we're doing. Next slide, please. Just our history. We were actually invited by someone by an existing customer of ours to work on Bo. And for a little background, we are one of the leaders in traditional Ethernet SerDes. Current products go from 1 to 112 gig. We support 16/7/6 nanometer today, and millions of units have been shipped. But as an order of magnitude, our SerDes range from about 4.5 picojoules per bit to maybe 6.5 to 7 picojoules per bit, depending on range and so on. And as you've heard from Elad and team, Bo at die to die is dramatically less. We're talking 0.3, 0.4, 0.5 picojoules per bit. So really 10 to 15 times as efficient, 15x efficiency gain. So that's the reason I think the market is moving in this direction. So basically, we've come in as being customer driven, and it's definitely a very exciting time to be in this space. We can't share too much details on our first customer. The second engagement we can talk about. We've started to work with QuickLogic, which is an eFPGA company. And we're looking to embed Bo /UCIe in their upcoming chiplets. So they will also talk about that. I think there's a presentation from Brian, the CEO, a little bit later on. So our involvement is very recent. We started in 2021, late 2021, and now I think we're a little bit more active. And we do want to reiterate that this standardization and what ODSA is doing is going to be a key enabler for this new market and getting it adopted. Next slide, please. So our use case is sort of very targeted. We talk a little bit about our 22 nanometer product, which is the first node that we're working on. And we're seeing initial targets of somewhere between 0.6 and 0.7 picojoules per bit. Obviously with 7/6, which will be available towards the end of this year, we'll be quite a bit below 0.5. And in 2023, we will be sort of looking at, you know, how to extend BOW, and we will participate in, I don't know whether it's going to be BOW 2.0 or whatever the BOW is. And also, you know, this new UCIe specification. So specific to the timeline, again, we will deliver our first solution in a few months, and the 7/6 towards the end of the year. Next slide, please. So I just want to share the good and maybe not so good. We like the fact that because of the market segment that we're targeting, that there is obviously link layers, but you can also bypass the link layer if you have some specific needs. It's also very flexible. You can do non-terminated or terminated. So there's a lot of flexibility. Bump pitches are flexible, so you can do 130 for traditional, or go all the way down to more advanced packaging. So our initial working experience has been that straight, simple routes, and especially streaming interfaces, like an Ethernet interface or a PCIe interface, are really prime and really work well in this environment, right? So I think the work on interoperability that Luchita is doing with D-Matrix is also so great. So the concept of eventually being able to interop is critical for success. We do see the 16-bit data limit on BOW as being somewhat limiting. The fact that as we go to higher speeds, there's no low latency effect currently defined. In one sense, it's good because we're going to use our own ultra low latency approach, but there may be a need in the market for something like that. And I just want to caution people that it's not like doing a PC board or whatever, where you just throw 8 or 10 chiplets on and you connect them with these BOW advanced interfaces and everything works. It's quite challenging. So we're targeting very close connections, ideally direct.
Got a 1 or 2 minute warning if you want to finish up.
Yeah. Next, I'll go to the next slide. Thank you. And so what's next? Obviously, we're going to be supporting 22/7/6 and 5/4 later on next year. And we are really working on supporting chiplets that connect to SoCs or FPGAs. We're focusing on 800 gig, 1.6 terabit, which is forthcoming across high-speed links, PCIe Gen 6, CXL3. Again, these streaming interfaces, we're putting a lot of effort and working with controller companies on putting these chiplets together. And we're also working on JSDD, which will leverage 64 gig SerDes on one side and BOW UCIe on the other. And then there's an emerging USB 4.2, which will use PAM3 of all things, across some slow speed links. Again, the focus is on, for us, is chiplets that will connect very, very, very easily to an SoC. Next slide. Yeah.
Okay.
That's it.
That's it. Wonderful. Okay, so thank you so much. That was great. So one of the things we really unique about the ODSA from day zero is that we're just not focused on connecting chips, but also on how information is transported across the chip between the chiplets. And our next speaker, Gary from NXP, was instrumental in our ODSA's second contribution to the OCP and it's a single company contribution from NXP to transport the AXI protocol between chiplets. But that's not what he's going to talk about today. I wanted to bring that up as a huge thank you for a really big contribution to the ODSA's effort. All right, Gary, who I believe I'm actually seeing for the first time.
Hey, everyone. Okay, thank you, Bapi, for the gracious introduction. So I'm going to talk about what NXP is doing regarding ODSA BO 256-PHY development. You can go ahead. So what is our motivation to use ODSA? Well, we are proceeding with an ODSA BO 256-PHY design in one of our current product technologies. And the intent is to validate and demonstrate readiness. So we think that the BO 256-PHY provides an opportunity for cost-effective as well as low latency multi-chip products. And how have we been involved in ODSA? Well, I was introduced to ODSA by Sam Fuller, who was involved in the business committee leadership some years back. And we brought a group of people to be involved in the BO-PHY as well as the link layer. And so Gayatri, Alvin, and Dekla have been involved in the BO spec development, and I've been more involved in the link layer area. Okay. So what is our product intersection? Well, NXP has developed a number of multi-chip products in the past, and will continue to do this. It's an accelerating industry trend. And we're still looking for intersection opportunities for BO 56 that are under consideration and being discussed. And specifically, we're starting this validation of BO 256-PHY with one of our older technologies, because it's one of our in use but older technologies, a 16 nanometer technology. Initially, it just makes it easier to do the initial development. And this design is nearing completion this quarter, and then we'll begin to do the layout and other implementation activities afterwards. So, and I think I'll give you some time back, Bobby.
Okay, thank you, Gary.
Sure.
That's right. I did forget about Sam. Sam was instrumental in while he was at NXP in helping this effort get going. Thank you for bringing him up. Okay. I don't see JP online. From JP, are you online?
Yeah, Bobby.
Oh, you are. Okay, wonderful.
Yeah.
All right. Okay. Our next talk is this really nice prototype that we're building. And JP has been, JP deserves kudos for actually building hardware entirely in the open. One of the few efforts that I know of that has done this with limited funding, no scale, and no budget, and still managed to pull it off. So fire away.
Thank you, Bobby. Good morning, everyone. So I'm here to talk about the open platform we're developing for BOW-PHY interoperability testing. And my name is Jayaprakash Balachandran, go by JP with Cisco. But here I represent the community. So whatever I say here is either community or my own opinions and not my employers. With that note, let's get started. The first is actually why chiplets and why this particular activity we are doing. Semiconductor scaling has been slowing down, and chiplets have been the proposed solution to address the scaling issues. The chiplets bring performance, power, and time to market benefits. And the shown here is a kind of a Strawman architecture for a chiplet-based design. And so you saw there several IP is being developed for BOW5. The BOW5 is interconnect between the dies or chiplet interconnects. And we expect the future integrated circuits to be composed of chiplets from multiple vendors. And and this, the success of these products, the integration from multiple vendors, just like how you do on the PCB, is really depends on the interoperability between this the chiplets from multiple vendors. So, so the interoperability is something that is required for any standard IO standard development. But what is the key challenge in this? Bobby, can you go to the next slide? And so before we talk about this in detail about interoperability challenges and what we do here, I want to set actually our high-level goal. And the high-level goal for this particular work is actually demonstrate the interoperability between the two BOW5s completely developed between two different vendors. And in the first phase, what we want to do is demonstrate the interoperability at the PHY level. And then and the subsequent phases, we go up the stack, the data link and transaction, the other layers, right? So with this effort, we hope to bring confidence to the adopters about the BOW specification. Can you go to the next slide? So let's talk back again what the interoperability testing challenges, right? So if you take a standard like PCI Express, the external IO interconnect standard, and so this actually comes at the very end. You make the development, and all you need to do is just interoperability is to either connect the different systems together, either at the connector level or at the wire level, and is just hook up things together and start testing it. Right, but whereas in the chiplets, it becomes more complex because the chiplets being the die-to-die interconnect, you need to develop a package for it. And then once you start developing a package, you develop the PCB and then start developing the software associated with it. So it requires a whole platform development, not just connecting the two systems together. Right, this brings quite a bit of challenge. And so here, the IP vendors are focused on the BOW specifications. They're focused on the chiplet development. They are putting a lot of efforts in verifying, getting this fabbed out. And they'll also be developing a platform for their own verification. And then they'll validate and characterize. And if they have to spend effort on the interoperability testing, again, it would add some effort like develop another platform, the package PCB and software within the third part with this, another IP provider that would easily add about 6 to 12 months of effort. So Bobby, can you click once? Yeah, thank you. So if you do this way, actually, that's the conventional way. So the interoperability testing comes after your detailed characterization because the IP vendors are focused on their own IP silicon, and this would add about 6 to 12 months of effort. Right. So what we felt, a lot of discussion, what we felt is actually we decided to do this effort, the interoperability testing as a community effort. And instead of vendors themselves or IP providers themselves focusing on the interoperability, we let them focus only on their chiplet designs. And the interoperability, we do it as a community effort. Right. It brings a lot of benefits. We bring people together, uncover any issues that we need to address in the standard. And also we plan to develop the implementation guidelines and software with it. Right. So overall, it's kind of win-win situation for the IP providers and any players in the ecosystem. Can you move to the next slide, Bobby? And so what are workstream goals, the BOW interoperability goals? First is actually we want to develop a completely open platform consisting of a package substrate, a PCB, and between two different implementations adhering to the BOW specification. And the other thing is we'll also agree on a set of interoperability and compliance tests. And then we also agree on the test methods, how this should be tested. And the other thing is we'll also take this opportunity to define a vendor neutral software APIs for testing. So this has been a problem across the industry. If you take any SerDes or any high-speed interfaces for that matter, every vendor has their own way of interacting with the register set and the software associated with it. It brings more complexity to the problem, and everybody does the similar functionality, but they have their own way of doing things. So we want to bring a standardization to that. We'll define a software APIs that actually helps in a standardized way of initialization, monitoring, and control test. Right, and we are also working a lot of work. We are also doing to developing guidelines for die-to-die layouts. For instance, there are some layouts, it's very straightforward. It connects between the two dies in a very straightforward fashion, but there are also a lot of other complex interconnect structure that one could encounter in the actual design. So we're identifying these kind of different cases, analyzing the performance.
2 more minutes, sorry.
2 more minutes, okay. And so we'll also publish the results as we progress. And so along with the detailed interop test reports. Can you go to the next slide, Bobby? Yeah, this is what we are developing, that so the high-level view of what the substrate looks like, and you can see the dies from 2 different IP providers, Blue Cheetah Analog and D-Matrix. And they are completely developing independent PHYs and 2 different technology nodes. And we'll take these dies and put them on a substrate for the interoperable testing. We'll also have these PHYs, BCA and D-Matrix PHYs independently tested as a reference. And overall, we'll have a rich set of interoperable test data, both on a short links as well as long links that cover the entire design spectrum. Can you go to the next slide? Yeah, so for this particular work, we leveraged that ODSA accelerated prototyping platform we developed last year and demonstrated in the November summit. And this particular platform is highly flexible and can easily implement this the interoperability, implement interoperable tests that we want to do on BOW PHYs. Can you go to the next slide? Yeah, this particular work would not have been possible without active participation from a number of companies listed here. And this list has been growing. So we have equal participation from a number of companies involved in chiplet designs, analog circuit designs, end users, and system designs and OSATs. So with this active participation, can you go to the next slide? Yeah, so we are making very good progress on the interoperability platform development. And so we plan to tape out the package sometime in July, the package part of it. And then the whole interoperability testing we'll plan to demonstrate sometime next year, early next year. Right. So can you go to the next slide? So in summary, this work particularly facilitate commercial deployments of this BOW PHYs. There are a lot of products being developed, and interoperability testing is one of the key requirements. And this work will facilitate. And this brings not only confidence to adopters, but also enable the early adoption of this particular interface in different products. And this particular work is completely community driven. And a lot of interesting work has been happening. If you're interested, definitely we welcome you to participate in our weekly calls and look forward to your participations.
All right, thank you. If you want a prototype developed on a shoestring budget, JP is your man. So as you can see, we've got IP vendors. We've got prototypes, community prototypes to support the IP vendors, and internal single company prototypes as well. And now we will make the transition to products that use the ODSA standards. And I'm going to start with Brian from QuickLogic, who actually is the only person to actually use the Zoom background that Archana provided. So kudos.
I follow your instructions, Bobby.
Well, Archana's, thank you. Here you go, Brian.
All right, thanks, Poppy. Thanks for hosting this and for the virtual background. Yeah, let me start a little bit about QuickLogic. Go ahead and go to the next slide. So QuickLogic is a FPGA company. We do FPGA, discrete FPGAs, FPGAs with processor cores, and we do embedded FPGA IP cores. And as such, especially with the supply chain constraints in the market today, a lot of our customers are coming to us and looking at how might they take more control of their own supply chain, not using discrete, but actually look at chiplets as a development strategy. And so we were getting inbound requests for how we might blend our embedded FPGA or make it more conducive to integration and chiplets for our customers. And so that's part of our strategy now, is to engage in that way on these products. And as such, we've been involved with the ODSA since 2022. What you can see in the bottom right there is just sort of a graphical representation of what an embedded FPGA core is. It's essentially a bunch of programmable gates, RAMs, and DSPs that customers can integrate into their ASIC design. Okay, let's go to the next slide. So what is the use case for this at QuickLogic? And I think you can kind of zoom out and say, what's the use case for programmable logic in general in these types of systems? And generally, the way we think about it is we think about the core and the uncore. So the core in these systems is going to be, you know, the heavy duty processing. If you think about AI machine learning use cases, there's a lot of research that's showing that these algorithms for AI ML are changing faster than silicon can be delivered to the market. Programmable logic is a great way to actually implement those algorithms now before you deploy your systems. And in the future, as those algorithms change, you can update the programmable logic in the field, because generally these are reprogrammable technologies. And so that's for the processor or the core use case. The uncore use case could be that, you know, a lot of the talks today have talked about how we do die-to-die interconnect and have it be standards-based. But more often than not, what our customers want is, after they go through the standard interface, they want something unique for them. And the uncore could be that you're doing some level of pre-processing on data before you go into the core, the heavy-duty processing. And so as such, that's what sort of drove the collaboration with Etopus to bring to market an FPGA-based chiplet that combines sort of the best of both worlds, where you have this high-speed standard for I/O plus the FPGA for programmability. The starting point, similar to Etopus, is on 22 FDX at Global Foundries, which was a node that we've supported for some time now. And we're under evaluation right now on lead customers to see how we might architect something so that the chiplet itself can be reused across multiple customers. Because as we heard from Rishi, no one size fits all. We completely agree with that. And ideally, we'd like to architect something that can be useful for multiple customers. And again, the primary use case here is for AI ML, both for the pre-processing of the I/O and the core processing inside. Next. So what is next at QuickLogic? So the beauty of the way that we do our FPGA IP design is that we have a very automated approach that leverages standard cell libraries from the foundries. So it essentially—
Yeah, hey, Anki. I'm doing all right. How about you?
Somebody needs to go on mute.
I'm doing great. Essentially what we can—
Wait, they muted Brian too. Hang on. Brian, you're on mute. Hold on. John, would you mind unmuting Brian or Kaylee?
Brian, it looks like you're self-muted right now.
Oh, Brian muted. Nope, still can't hear you. No, no voice yet. We got a problem. All right. Huh. Okay. Can anybody else hear Brian, or is it just me?
We can't hear him.
Okay.
Can you hear me now?
Yes, we can. Oh,
Okay.
wonderful.
So the beauty of what we have at QuickLogic is we have an automated IP compiler. So any standard cell library we can get from the foundry, we can knock out an FPGA core very quickly to target basically the node and foundry that our customers are at. You can see on the right the amount of logic elements that you can get on the various different technologies that we're either already delivered on, like 22 FDX, or evaluating like the more aggressive FinFET nodes at TSMC. And I think that that is the last slide.
All right. Well done. Thank you for coping with the hiccups. Appreciate it.
Thank you.
And I think one of the most exciting things about ODSA right now is the number of new companies we have joining us this year, QuickLogic and others. Steve or Sohail from DreamBig, are you on by any chance?
Yeah, this is Steve.
Oh, perfect. Another new entrant in 2022. So, okay.
Okay, great. Thank you, Bapi, and hello, everyone. So I'm Steve Majors with DreamBig Semiconductor. We're building a chiplet platform for data center SmartNICs, also known as DPUs and IPUs. Go to the next slide. So we're supporting chiplet die-to-die solutions that meet the criteria of being standards-based, have high bandwidth and low latency. We define that as at least 16 gigabit per lane and less than 10 nanoseconds, including the link layer. Also support low-cost packaging, meaning RDL fan-outs or organic substrates, but without silicon interposer. And we find that the ODSA BOW standard meets all of these criteria, and the advantage is that it's productizable today. So we've been a member of the ODSA for over a year. We're primarily a background contributor. We work through collaboration with industry-leading members, Alphawave and Blue Cheetah. And we are also developing an ecosystem that's got more than 10 customers and partners in it currently that are all actively working together to develop interoperable chiplet technologies, chiplets, and products for data center markets. Next slide, please. So we're using the BOW for die-to-die links that are between server class chiplets. These tend to have multiple interfaces on each chiplet. Each of the interfaces comes in multiple slices, where a slice is 16 lanes of that 16 gigabit standard. And this gives us terabits of bandwidth that we use for standard transactions across those various chiplets. We're using this platform to develop DPUs in the case of DreamBig specifically, but also CPUs and accelerator solutions with our partners. We'll be showing leading performance per dollar per watt with these solutions, with silicon tapeouts that are currently in progress and early samples of the first use cases early next year. Next slide, please. So what's next for us is that we're productizing an open DPU platform. It includes a rich ecosystem of BOW compliant chiplets in low-cost packaging. We're making these DPU chiplets in a way that they're retargetable to other markets such as CPUs, accelerators, and edge, where similar I/O and networking requirements that we use in the DPU are also needed. And we're easing the adoption of the ODSA BOW standard by providing complete reference solutions that include our chiplets, our package designs, board designs, firmware and software, and so forth. All of the collaterals that customers that wish to build their own silicon solutions would need and can benefit from. So on the bottom of this slide, I have some examples. On the left, the types of chiplets that we're developing ourselves and with our ecosystem partners. DreamBig is developing I/O hubs and networking chiplets. And then partner companies are building compute and FPGA and accelerator chiplets. And we compose those into products, as you see in the middle, where in the case of DreamBig, we're composing SmartNICs that perhaps don't have a computing element on board, as well as DPUs and IPUs that have a combination of I/O networking, and then any one or a combination of those three partner chiplet types. And then in turn, this group of more than 10 companies take our chiplets and then compose their own products. Examples being CPUs, FPGAs, and TPUs. And then what you see on the far right is customers that have adopted the chiplets that are being developed by us and the ecosystem partners are able to compose their own products. So for example, they may use our I/O, but develop their own networking chiplet, or in the middle of the right-hand side, their own computing chiplet, or a combination of both. And then we have extreme cases like in the far bottom right corner, where customers are composing extremely complex systems that have large instantiations of a variety of these chiplets. All of the examples that I'm showing are real world and in progress. Thank you.
Oh, that's it.
Yes.
Okay, thank you. So our presenters are turning out to be incredibly efficient for a multitude of brief talks. So if you have any questions, we'll try to get our contributors to answer them at the end. So please type them in the chat window. Next speaker is Mr. Finnegan from Metronome.
Okay, I must be in trouble if Bobby is introducing me as Mr. Finnegan. Okay, first thing to note is we have two companies. Let me just explain. Metronome has developed several generations of SmartNICs over the past decade. And Corigine recently acquired the rights to certain Metronome IP. Together, we are building the next generation SmartNIC, the fourth generation SmartNIC. And I, for my sins, am the EVP responsible for delivering that silicon. Next slide, please. Rather than during the course of developing these prior generations of SmartNIC, we've, I think, learned a few things. And I guess we view there are certain attributes or properties of the fourth generation SmartNIC that are really important. One, of course, is the flexibility and the flexibility afforded by the use of chiplets and different types of chiplets. For example, an I/O chiplet, a data path processing chiplet, management plane processor, and obviously, we've heard already about some of the chiplets that may support ML or AI. These all must be able to be composed together, and of course, not just from third parties, but also from different foundry nodes. In order to do that, you need open standards, and that's why we've been active at the ODSA adopting the bunch of wires interface. But also in the course of developing previous generations of product, we've perhaps come to realize that you also need an open instructions, particularly for your...
I think I'm the only one in the afternoon.
Okay, sorry, Jim, we've got an interrupt again.
No problem, no problem. Particularly for your programmable data path. The other property, of course, is that typically one wants to scale from, perhaps even just 2 by 25 gig up to multiple 100 gig interfaces. And so you need to have a design that can basically scale, dimensioning your processing requirements for the offered load from those different interfaces, all the while ensuring that you don't block or drop any traffic, and including the ability to support very large packets, such as greater than jumbo packets, a prospect which has been much discussed at the Linux Forum. Linux Foundation, rather. And of course, perhaps the biggest motivation of all for the chiplet approach is the power performance area equation.
Sorry, I'm trying to go up mute. Sorry, can you repeat again on the VRMA? You are the only one that pulled the smart lock, which is yes, that's correct. I'm aware on that one.
Kaylee or Michael?
I guess we have someone actively selling their technology, which is great. So we've been involved with the ODSA for basically since its inception, and we've been long evangelists for the approach. And rapidly, at a drop of a hat, quote such things as, Amdahl's law, 1 gig I/O requires 1 gig of processing. How are you going to do that? That probably means you're going to have for multiple 100 gig interfaces, lots and lots of MIPS. How are you going to do that? How are you going to do that with an FPGA? How are you going to do that with a monolithic device that is, very expensive relative to the yield and power performance area benefits associated with chiplets? Next one, please.
And Jim, I noticed you skipped over the fact that Metronome was the company that's one of the founders or the motivator for ODSA. So
I was being modest. And I know it's an unusual trait. I think jumping to the very specific practical implementation that we're doing. This is an example here, and what you can see that the small chiplet is basically an I/O chiplet, small except, for example, the number of SerDes, 112 gig SerDes, is more than 20. It supports PCIe Gen 6 plus a tuned Mac controller that can basically support very large packets without any blocking. On the right-hand side, you see the processor chiplet, which is essentially a pool of small RISC-V based cores. There are, in fact, over 1,000 of these per chiplet. And as you can see, there's an interface, a bunch of wires interface between the I/O chiplet and the processor chiplet. And then at the top and bottom of the processor chiplet, similarly, there's a bunch of wire interface such that you can add more processors in order to, as I say, dimension the amount of processing that you need to support the offered load. So, and I guess one other lesson that we've learned over the course of the past decade is that the programmable data path must be organized by this large pool of small cores that are organized in a MIMD type configuration, where also perhaps referred to as a run to completion model. We're basically doing this. The development is well underway, and we're targeting the TSMC N6 node, and product will tape out in the first half of 2023. We're also, to ensure correctness, A0 correctness, we're very much emphasizing upfront emulation, and we're basically using the Corigine Mimic emulation platform, which is a new entry into that market. We're using that as the vehicle to ensure correctness. Next one. And I guess, the obvious question is, what's next? Well, I think like everything else, as I say, the proof of the pudding is in the eating. So rather than talk about standards and adaptation and problems associated with making it all work, we're actually going to do it. And we're very much, planning to, showcase what we're doing as a justification and empirical proof that this approach works. The other key point, I think, here is we're also working with the ODSA with a view to, propagating the whole philosophy and approach in the APEC region and making, our chiplets and basically providing a platform for other people to land their chiplets on the Mimic platform. So that's the message, upfront proselytizing, adaptation or adoption of the standards. Now we're building product and shipping them next year. Thank you.
All right. Thank you, Jim.
Sure, Bobby.
Our final speaker is, if I can get my screen back, is Wensin. You're on, right?
That's right. I'm here.
Yeah, thank you so much. Okay. And one of our strong supporters right from their day zero on the prototyping effort.
Thanks, Bobby. This is Wensin. Good morning, everyone. I'm Wensin from D-Matrix. So I'm going to present today's the bunch of wire die-to-die interface for multi-chiplet AI system we are currently developing at D-Matrix. Next, please. So first of all, a bit of background information regarding D-Matrix and ODSA. D-Matrix has been actively participating in ODSA since year 2020. Using ODSA bunch of wire, D-Matrix basically designed die-to-die interface for parallel multi-chiplet communications. So in this use case, D-Matrix derived the design based on bunch of wire design specifications. The example link channel and channel link simulation experience shared among the ODSA community really helps in the circuit design and implementation at D-Matrix. In return, D-Matrix contribute to the ODSA by sharing our design experience. This includes the actual circuit implementation feasibility. In addition, D-Matrix also fully support the interoperability proposed by the ODSA. So this also includes the technical support for interoperability studies JP mentioned earlier on. Next, please. Before I talk about D-Matrix for product, let me also give you a quick introduction regarding D-Matrix. D-Matrix is an AI company founded by Sid and Sudeep about 3 years ago. Both of them have more than 20 years of silicon and system experience. With proven record, they delivered more than 100 million chips in the cloud and enterprise industry. The product generated more than $1 billion in total revenue. Our current D-Matrix team consists of 55 very talented persons located at Silicon Valley, Sydney, and Bengaluru. As of today, D-Matrix has raised $44 million from our investor, including Playground, M12, Nautilus, Marvell, Entrada, and SK Hynix. Next, please. So as an AI company, D-Matrix basically built AI compute products. The figure at the top basically gives you an idea of what we are doing at D-Matrix. From single AI neural core, we design AI engine and then further scale them and integrate them into multiple AI engine into a single chiplets. Using fabrics of chiplets, we deliver different products and scale them for different applications. So the figure at the top right-hand corner shows the proof of concept Nighthawk AI platform silicon we announced last year. On the other hand, the figure at the bottom right-hand corner is the next generation crosshair chiplets that we are developing. As you can see from the figure at the right-hand side, these chiplets incorporates 3 sets of bunch of wire die-to-die interface. This die-to-die interface basically allows us to link multiple chiplets together and then scale them into an even more powerful multi-chiplets AI system. Next, please. So the figure on this slide shows an example at chiplets crosshair AI system we implemented on a single common substrate. The blue line you see on the figure between the chiplets is basically the die-to-die interface linking multiple chiplets together. Here, all the chiplets are connected through bidirectional interface. If we were to zoom in into one of these connections, you can see on the right-hand side of this page how we actually utilize two pair of the die-to-die interface in order to achieve the high-speed 512 gigabits per second data communication links that's needed for our applications. In this case, we choose to use ODSA bunch of wire because of the low power architecture in terms of picojoule per bit. In addition, the high bit shrunk bandwidth and support for cost-efficient organic substrate also fit nicely into our requirement. More importantly, the proposed interoperability basically enables heterogeneous integrations. In other words, the chiplets you see in the top figure doesn't have to come from D-Matrix. It can come from different parties, vendors supporting various functions and features. Next, please. So in order to make all this happen, we also developed die-to-die interface at D-Matrix. The figure at the center of this page is the bump map of the die-to-die interface. This die-to-die interface will go into one of our test chip, and various channel settings will be verified using the test spot example shown on the left-hand side. So allow me to also give you some detail about this die-to-die interface that we are developing. First of all, it is designed using TSMC 6 nanometer technology. It has 16-bit single-ended data bus. Each of them can operate up to 16 gigabits per second speed. Overall, it achieves an energy efficiency of less than half a picojoule per bit. The bit shrunk bandwidth is 0.19 terabits per second per millimeter for a single stack design, and this can be scaled up to 0.75 terabits per second per millimeter for a 4-stack design. And we are expecting the silicon test chip in the 4th quarter this year. Next, please. Going forward, D-Matrix will continue to contribute to the future development of multi-chiplet interface. In this case, we target to achieve higher bit shrunk bandwidth of greater than 1 terabits per second per millimeter. We also want to improve the energy efficiency to less than a quarter picojoule per bit. In addition, we also want to design the link layer meeting all the compliance and interoperability specification. Last but not least, we also excited to explore implementation using more advanced packaging technology, for example, interposer or integrated fan-out. And I think this is all I have for today. Thank you for your attention.
Oh, wow, that was perfect. Thank you.
Thanks.
Okay. A huge thank you to all our presenters. I think, John, believe it or not, I believe we're a few minutes ahead of schedule. So if anybody has any questions, you can either type them up into the chat window. Almost all our presenters are online. I think they'd be happy to answer your questions. But if we don't get any, we give the time back to John. Going once. Okay. Well, in that case, what I'm going to do is invite everybody who's done a lightning 7-minute presentation here to do a 30. Oh, we have a couple of questions.
We got one question, yeah.
Oh, wonderful. Will the presentations be and or video be posted later? I think that's a Kaylee or Archana question.
Yes, if you scroll all the way up, Michael answered that question a couple hours ago. They're going to be all the Tech Talk recordings will be posted at OCompute events, past events, which you can get to from the OCP main page.
In terms of how do we see UCIe alignment happening? First off, there's a lot of excitement that UCIe is happening. And what we see is we see the potential to overlap, and there's a lot of interest. There's some areas in which we're completely complementary. In fact, there's a lot of work in our CDX group, which is actually being driven by explicit requests from the UCIe consortium. And so where there is some overlap, like in the specification of the D2D interface, what we hope to do, there's a decent amount of participation overlap, especially in the larger companies between UCIe and ODSA. So we're hoping to use that to get some commonality. We've had some tangible, concrete technical thoughts in that space. And Elad has volunteered, and a couple of other people have volunteered to sort of translate those into a more concrete alignment going forward. Elad or DJ or anybody else, if you'd like to speak up, please feel free to do so.
Yeah, no, that sounds about right. I think the hope is that we can drive things in a way that indeed there'll be compatibility that's created. And as you saw, obviously there are a number of ecosystems forming around various ODSA standards already. Both BOW and OpenHBI. And so the hope is indeed that we can get the world to the state of there is a de facto standard, and it technically looks similar to all the things that people have learned and developed and made work for the right purposes.
And I'd like to point out that the ODSA effort is not just a die-to-die PHY effort, but it's a protocol effort. It's an ecosystem effort. It's a workflow effort, business. It's a fairly comprehensive, fairly comprehensive set of activities. In fact, one of my great, we have a business work stream that's produced a first of its kind chiplet cost model that's entirely open source. We wanted to focus this on commercial products. We have a die-to-die PHY comparison spreadsheet that is an industry standard. We have the CDX group producing workflows that are also references, say, for power modeling. And one of the other things we're really good at is publishing our work and referee to conferences and technical journals. So it's a comprehensive effort, just far beyond just the PHY layer or even the protocol stack. So there's plenty of room to align with other participants. Any other questions? Or would any of our participants like to say anything else that we haven't covered today? Any of our speakers, since we've got about 2 to 3 more minutes. Okay. In that case, thanks everyone. It was very kind of you to put put the slides for your participation together. I will invite you and see if I can schedule you for longer 30-minute talks at our weekly Friday meeting. What is the max number of chiplets per socket, or what is a max socket DIMM? Anybody who's actually building a product want to bite this off?
We have seen, this is Rishi here, we have seen basically designs which have 7 to 8 chiplets on a single package. This question is very open-ended because it depends upon the limitations on the packet size and also what is your parent die size. You can have the whole tile of designs on chiplets by itself. So, but we have seen in a commercial deployment 7 to 8 chiplets with hooked onto a parent die. But that doesn't set the maximum limit, but this is what we have seen so far.
And Wensin, you had a decent number of chiplets on one substrate, right?
Yes, that is correct.
Elad, Gary, anybody else? 700 watts max dimension. Hopefully everybody's seeing the question.
Yeah, no, I mean, I think there's a physical substrate size question, which, you know, on the GAC magnets, you can get pretty big. And then I think, yeah, I guess in terms of number of chiplets, as I suspect maybe Winston's about to say, right, one could imagine building a system with, you know, a very large number of very small chiplets. Whether or not the market partitions that way is maybe a very different question. So I maybe sort of return the question on what is the particular system you have in mind. But yeah, I mean, 8 to 10, you know, seems you know, fairly standard, so to speak, you know, maybe on the high end. But yeah, if you imagine something, you're trying to build a composable system with lots of smaller chiplets, I could certainly see that number from a chiplet count perspective could be much larger.
Yeah, I think Elad, you answered it correctly. So I think the point is about the interconnect on the package itself, right? You know, there is the limitation is caused by that. There are direct connections between the die, and that's the limitation certainly that the foundries have imposed or OSAT have imposed to kind of maintain the equal distance wires. So essentially, you know, if you're building a metric of all the different chiplets, you can put so many of them as long as they're all connected direct straight wires. The limitations that Rishi brought up is about the IO chiplets. You know, you have a main technology die in the center, and then you have all these IOs around it. That's where, you know, the limitation comes in to maybe 7 or 8, 2 on each die edge.
Okay, I'm going to stop sharing. We have one more question, but I think we can save that. Hey, I encourage whoever's asking the question to please come on our Friday meetings. They're pretty raucous and open-ended. So Brian, John, it's all yours. And then thank you to our community. So I want to say thank you to everyone who participated and our regular quota of contributors.
Thank you, Bobby.
Thank you.
Thanks, Bobby.
John's on mute.
Oh, I said all of that on mute. All right, let me start over again then. Yeah, thank you, Bappy, for putting that together. I know it's a lot of organizing to get this diverse group of companies together and get presentations to them, get them all here at the same time. So that was a really good presentation. Thank you a lot for that.
Thank you. Thanks for being patient to you, Archana, Kaylee, Michael, and of course to the presenters.
Yep. All right, that's all we have on as far as topics today. Just do a little bit of wrap up. You know, like to get some feedback on the server project and what everyone thought of this tech talk and what we think the server project can do better, or any of the suggestions for the server project in general. As usual, you get too many people on the call and nobody wants to speak up. We are definitely you know, taking any kind of feedback on if there's something we should focus on more that we're not focusing on, or if there's another sub-project that there's enough interest in to get started up on. There's also discussions on the different OCP communities we collaborate with. I know tomorrow's Tech Talk is going to focus on modularity with some new specifications and collaboration with hardware management group who's doing the DCSCM, the secure control module. So we're definitely doing a lot of collaboration with them, but there's other groups that we could collaborate with more as well. Call to action, stay involved. If you look at, we do have a mailing list that we send out all of our invites and agendas to, and there's a separate mailing list for the 4 different groups. Join the calls. We have the OCP projects calendars. I know I said this when we started, but a lot of people would say, well, how do I find out where the calls are? If you go to projects and whichever project you're interested in, and you scroll down, all of these calls here are server project calls. The main one for the server project is the 4th Wednesday at 8 a.m. Pacific or 10 a.m. Central with the call-in information here. So any of the calls you want to go to, they're all listed on the calendar. There's call-in information for all of them. Want to thank our sponsors thank Google and Meta and Intel for sponsoring this and keeping our costs low and keep this as a free conference, or not conference, free Tech Talk series. It's a lot of effort to get these organized and arranged. So definitely want to thank our sponsors for that. And we are about out of time. Want to definitely encourage everybody to join tomorrow's day 2 Tech Talk. Let's see, I have a agenda for that hidden. We should pop that up for those who haven't seen it. So tomorrow we'll be announcing a DC MHS spec, our modular hardware system. It is a group of specs that has 6 or 7 subspecs in it, and that it does coordinate with the DCSCM to make a whole modular system. So I know there's a lot of excitement about that coming up tomorrow. So encourage everybody to come to the day 2 talk tomorrow. And that's all I have today. Anybody have anything else they want to say before we close the call? Anyone on the OCP Foundation want to give any extra closing remarks?
Yeah, John, just want to pop in and thank you for the work that you've done here, and we'll continue to do for the server project. And I know we've got Mark Shaw on as well. Mark's a new server project co-lead along with John. So really excited to see this project continue to move forward.
Yeah,
great. Thank you all so much. Have a great day, everyone. We'll see you tomorrow.
Yep. See everyone tomorrow.
All right.
Thank you. Goodbye.
Thanks, guys. Bye.